In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMECA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMECA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMECA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMECA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMECA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMECA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMECA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMECA, Science and Metrology Solutions.
Atom probe tomography. It's the only material analysis technique that offers both 3D imaging and composition measurements at the atomic scale. And it's contributed to significant advances in science. Here's how it works. The solid material being studied is prepared in the shape of a needle, with an end radius between 50 and 100 nanometers. That's 10,000 times smaller than the width of a human hair. The needle is frozen at a temperature colder than the dark side of the moon to hold the atoms in place, and is biased at high voltage, between 1 to 15 kilovolts. As a result, the sharpness of the tip and the high voltage induce an electrostatic field at tens of volts per nanometer, right at the tip's surface. Then, through laser or high voltage pulsing, one atom at a time is removed from the surface by field evaporation and projected onto a position-sensitive time-of-flight detector. Here's what that does. It allows you to simultaneously measure 1. The XYZ positions of the ion impact, and 2, the atom's time of flight, which can identify the element. Together, these pieces allow you to create a 3D reconstruction of your sample with up to 80% detection efficiency. Put plainly, APT gathers valuable data that's otherwise hard to obtain, providing information that other methods can't. Information, for example, that enabled higher efficiency LED light bulbs, significantly reducing electrical consumption worldwide. CAMECA is the exclusive manufacturer of atom probe tomography technology. Our LEAP and ICOS instruments are at the forefront of material science research. Want to learn more? Download our atom probe tomography tutorial, a practical introduction to the APT technique, or have a look at the 2018 Materials Research Society webinar, An Introduction to Atom Probe Tomography and Its Applications.
Close your eyes. What do you see? Do you see yourself, the path in front of you, the next step? Do you see your ambition, the cutting-edge approach that opens new dimensions in medicine, the biggest miniaturization that lays the foundation for the digital revolution, the holistic perspective that transforms humanity for good, the progressive vision that changes everything, the way you see the world, the way you capture moments, the way you transcend knowledge, the way you define precision and productivity, the way you live, move, love, heal, think, are. Open your eyes. Can you see it? Together, we are challenging the limits of imagination. For those who see beyond. Zeiss. Seeing beyond.
Hello, everyone. Perhaps a quick sound check before we will start with the afternoon session. Can you all hear me loud and clear?
Yes.
Yes.
Okay, thank you. Wonderful. Okay, it's 1 p.m. again. Hello, everyone. Welcome to the 5th technical session today, Functional Materials. My name is Florian Vogel, and I'm speaking to you from Guangzhou in the south of China. It is my great honor today and a great pleasure to be sharing this session with 7 talks that we are looking forward to until the next break. Before we start with the talks, I'd like to make a quick announcement regarding the timing today. The afternoon break time is extended by 10 minutes to 15:30, and I will remind everybody again at the end. So now let me introduce our first invited speaker today, Professor Tong Li from Ruhr University in Bochum, Germany. Professor Tong Li is currently a full professor at Ruhr University in Bochum at the chair of atomic scale characterization at the Institute for Materials. She got her Bachelor's of Engineering at the Beijing University of Aeronautics and Astronautics, her Master of Engineering at Queen Mary University of London, and her Doctor of Philosophy under the Atom Probe original George Smith at the University of Oxford. Professor Li has published over 60 peer-reviewed papers, many of them in prestigious journals like Nature Science, Nature Communications, Angewandte Chemie, Acta Materialia, with close to 3,000 citations. Professor Li's career has been steep and award-winning. In 2006, she got the prize for Best Graduate Student and Best Thesis in the Materials Science and Engineering Department at Queen Mary University of London. In 2007, she got a PhD scholarship from the Engineering and Physical Sciences Research Council. In 2012, she was awarded with a knowledge transfer scheme. And in 2016, she was awarded the prestigious Alexander von Humboldt Research Fellowship. She has been at various labs around the world at the University of Sydney, the Australian Centre for Microscopy and Microanalysis at the University of Queensland, and in 2016 joined the Max Planck Institute for Iron Research as Humboldt Fellow. In 2017, she became junior professor at the Ruhr University of Bochum for characterization of high-performance materials at the atomic scale, and since 2020 is a full professor at the chair for atomic scale characterization. Her talk today is about the characterization of active hydrous oxides formed after oxygen evolution reaction by a multimodal approach. And with that being said, Professor Li, the stage is yours. Would you please share your screen?
Thank you. Thank you very much for this introduction. It's kind of my whole life was being described. Thank you for these efforts. Yeah, we are still like 2 minutes earlier, or maybe I try to share my screen. Is the sound quality okay today?
The sound is perfect.
Can you hear me? Yeah, that sounds good.
Yes,
and you can see my screen now?
Now I can also see your screen. I think everybody else can see your screen as well. Would you like a reminder when you have 2 or 3 minutes to go, or your timing is perfect and I won't say anything? And
sounds good. I think 2 or 3 minutes reminder, that would be great. Yeah.
Okay, wonderful. Yeah, I'll do that.
But yeah, it's more or less 29 minutes anyway. Yeah.
I'd say that's a good morning to Germany. That's where you are right now, right?
Yes, exactly. Yeah, it's around 7 p.m. 7 a.m. Yeah, good. So I think now I will wait for 1 minute and we start, because the schedule was 7:05 or.
Okay, let's stick to German precision timing and start at 1:05.
Sounds good. Oops.
Okay,
So I
I think we
think
should
I
be
will.
good to start.
Yeah, exactly. Yeah,
You-
good morning.
Okay.
Good afternoon, everyone. My name is Tong Li. As Florian introduced, I'm from Ruhr University Bochum in Germany. So today I will talk about how we combined APT with the spectroscopy and the microscopy to understand how the evolution of this hydrous oxide during the oxygen evolution reaction. Okay. So the OER basically takes place at the anode side of a device called a water electrolyzer. And this is a device we use to produce hydrogen. And during the OER and a lot of dynamic process happening, essentially, if we take a close look at the anode side and we have the electric catalyst here and the electrolyte is surrounded with the electric catalyst and you have this solid and liquid reaction. And OER takes place at a relatively higher potential. And because of such a high potential, this can induce a dynamic, dramatic surface changes during a reaction. And such changes can be an oxidation state change because of the absorption and oxidation, and it can be dissolution of certain elements. And because of dissolution, it can cause the surface become amorphous, or because of the dynamic process, it can redistribute the elements and making the composition change. So essentially, all this aspect can really affect activity and stability of this catalyst. So essentially, if we prepare electric catalyst and during the OER, and they can be activated and being deactivated. So therefore, this is very important to link how does the surface change with the performance during the reaction in order to understand this activation and deactivation process. And when we're looking at this sort of different information, oxidation state, dissolution and structure, composition, etc., we cannot obtain such information by using one technique. So it is important that we combine different approaches to understand and have a whole picture of what is going on the surface and link this structural information with the performance. So I will give you a couple of examples how we combined a different technique to see how the surface changes. So for the first part of the talk, I will focus on is this material called Beta-COH. And you can see that this is basically a 2D layer structure of a material. And for each single slabs, this is called the slabs, and each single slabs was composed of the COOH octahedrals, and in between the slab, there is a protons. And this is one single unit of this Beta-COH, and you can see that in the slab distance is rather large, it's 4.4 angstrom, and you have to remember this number as I will recall this later on. And essentially the ions or electrolyte can go into the slabs and cause the intercalation, de-intercalation characteristic of this material. So therefore, this is very good for the electric catalyst, and also is very good for battery function. As you know, beta-NOH or beta hydroxide is very good pseudo capacitor material. Okay. Yeah, so in the first part of the talk, I want to understand how this Beta-COH evolved during the OER and how this temperature evolution affects the OER activity. And in this part of the talk, I will combine SPS, TEM, and APT to investigate this evolution. How we prepare the Beta-COH. This is, you can use the white chemistry method to prepare this single like platelets particle thing. On the other hand, you can electrochemically oxidize cobalt and gradually form the COH. And based on the Povich diagram, this is the diagram you can find out the stable state of the cobalt at different potential. So essentially, at a fixed pH value, as we increase the potential, we can gradually oxidize CO to COOH. So what we did here, we bought cobaltware and we encapsulate in a glass capillary. and then making this a kind of like a cobalt macroelectrode. So if you look at the surface of this cobalt, is only 125 micrometer as a diameter, and we use it as a macroelectrode and put in the electrochemical devices and keep cycling this cobalt electrode, and hopefully be forming this COOH during the oxidation reduction process. So the condition is used at this potential range, and in the KOD and D2O, I will talk about later when I use deuterated electrolyte. So this is the CV data, this is cyclic temperature data, and summarizes the OER current density and also the overpotential at 10 milliamps per centimeter square. So essentially, if we look at the plot here, after 30 cycles, as the OER current density reached the maximum, at the same time, the potential is lowest, and it means that at this state is the most active state. And later on, after 100 cycles, it's becoming deactivated. So as a comparison, in order to understand what is going on between 30 cycles and 100 cycles, I also prepare the sample at 1 cycle and 10 cycle to see what is the surface state after cyclic temperature measurement. So this is the SPS data, is essentially gave us the oxidation state, and also we can use this oxidation state to track what exactly the species will form after the CV cycles. So if I look at the SPS data, essentially below this 10 cycles, we gradually oxidize the CO to cobalt 2+, which is a hydroxide. And after 30 cycles, we're forming this 3+ COOH, which is, I call this cobalt oxyhydroxide. And it's very interesting to know, basically at 30 cycles, we have this oxyhydroxide. And as the CV cycle number increases, we still have this cobalt 3+ oxyhydroxide. However, the OER activity decreases. So essentially what we're trying to understand is we form this COOH on the surface after 30 cycles, super active, and as the time goes on and becoming deactivated, and why this happens. So we use the TEM and APT to investigate the structure and chemical. As you may know that if say we have this cobalt substrate and we allow this to have a CV cycles, we allow this formation of the COOH, essentially different facets can form different facets of COOH. And this is the second part of the talk. But the first talk, you just need to remember, in order to have this temporal evolution comparison of the structure and composition changes, we prepare the sample only from the 001 cobalt, and we can use this ABSD mapping trying to track where do we prepare the APT and TEM specimens. So this is the APT data for 1 cycle, and you see that this top part is this red color dots is the oxide species, and we also place a cubes in order to have a 2D concentration map of oxygen to see the oxide layer, and on top of it, as you see this the maps here, and we're trying to overlap the D2O with this oxygen 2D mapping and the OD with this 2D mapping to have an idea how this hydrous layer looks like. As you see, this is 1 cycle CV after 1 cycle, after 1 CV cycle, this is how this looks like. And after 10 cycle, very interestingly, this is the oxides that are propagated on the surfaces. If you're looking at this top surface layer, is the hydrous layer only occupy half of this oxide layer, and the bottom part doesn't have this water molecules and hydroxy groups. And this becomes very obvious after 30 cycles. The top surface is really hydrated, full of water molecules and hydroxy groups, and the bottom layer is free from the hydroxy group and water molecules. So essentially, we call the top layer hydrous layer, the bottom layer anhydrous layer. And such a anhydrous layer really disappear after 100 cycles. You see that you cannot tell the difference that much. So I talk about, say, we use this D2O and OD to do the CV cycles. And essentially, the reason for this is I'm trying to quantitatively understand how much hydroxy group and water molecules was kept in this hydrous layer. So in order to do this, I'm trying to avoid, say, these peaks that coming from water, that because of the sample transfer, it can also say the hydrogen was combined with oxygen and forming the OH2O, H3O peaks. Essentially, this is causing us to not accurately to quantify the information. So therefore, we use OT and D2O. But nevertheless, if you're looking at the mass spectrum of this hydrous layer, we still have a peaks of 17, so essentially 18 and 19 peak can be mixed with OH2 and OH3. So how we solve this OD and D2O more kind of in a more accurate way. So we utilize the peaks at the ratio at 1 to 3 for hydrogen H2, H3, and trying to understand maybe this is a correlate with the ratio of OH, OH2, and OH3, and then we can subtract the total amount of a peak count at 18 and 19 DA and to get the information of OD and D2O counts in the hydrolase layer. So this is the number of counts we summarize, and we can see that at 30 cycles is really highly concentrated with OD and D2O, and after 100 cycle, and such a hydroxy groups and water molecules really disappear. And we can also use ion concentration profile to get the oxygen to CO ratio. You can see that as the CD cycle increases and this oxygen concentration gradually increases. And next we use the HRTM, actually it's a HDF stem, to see the structure change for this hydrolase layer. And because of the dark contrast of this HDF stem, and we use the inverse FFT, essentially these orange color spots represent this beta COH structure. And the blue dots is the cobalt matrix. If you do the inverse FFT and you see the surface hydrolase layer is actually composed of these nanoclusters. So we have this formation of the nanocluster beta COH here. At the same time, if we measure the lattice constant of this beta COH layer, and by looking at the reflection spots, we see that the interslab distance here is 4.8 angstrom. If you remember that at the beginning, we talk about the interslab theoretical value of the interslab distance, something like a 4.4. So essentially by using APT, we see that at this 30 cycles, this hydrolase layer is full of a hydroxy group and water molecules, and this can expand the interslabs and making the expansion of the interslab distance to 4.8. And after 100 cycles, if we do the similar thing, and these orange spots represent the beta COH, the blue spots represent the cobalt matrix. If we do the inverse FFT of the orange spots, we see that, interestingly, this beta COH hydrolase layer become a monolithic film instead of a nanocluster. So essentially, from after 30 cycles, there is a morphological change. At the beginning, this nanocluster is super active and super hydrated, and later on, it lost water at the same time it become a film. Again, they're trying to measure the interslab distance here. We found out the interslab distance was contracted to the theoretical value, something like a 4.3, and this is related with the loss of hydroxy group and water molecules. So essentially, what exactly can happen during this reaction, what happens to this active beta COH? So before, because we transform the beta COH from the 2+, so there's a 2+ to 3+ oxidation reduction process can involve as a dissolution and redeposition process, because it's redeposition and at beginning is forming these nanoclusters of this beta COH. During the formation of the nanoclusters and the interface between nanoclusters can really serve as a fast penetration path. So they're letting the oxygen, letting the hydroxy group and water molecules penetrate across the interslab and expanding the interslab distance. And then it's becoming super hydrated and super active for the OER. But as the time goes on and we keep oxidation reduction of this beta COH, grows further and it grows as a thin film. And also it wants to stabilize the structure, and therefore it's contract of this interslab distance and pushing out the water molecules and hydroxy groups and making the interslab distance back to the theoretical value. And only the surface size is available for the electrolyte, and then the activity becoming decreased, and therefore we see an activation and deactivation process for the beta COH. So essentially use the APT combined with TEM to see the morphological and compositional change during the OER, and to resolve this why the beta COH become active and why this is become inactive during the as the OER proceeds. So this is the first part of the talk, and this is actually not the first study. We use this a multimodal approach to understand what is going on for this hydrolase layer formed during OER reaction. And back to the days, I also combined with scanning flow cell APT&M. This is the technique. You can see the online dissolution rate of the iridium. So this is a project about we prepare a nanocrystalline iridium film and we perform the conventional electrochemical test to see the activity and use the SFC APT&M to see the dissolution rate, which is the stability of this material. And then we use an SPS to look at oxidation state of the post-OER specimen. And by using APT, we resolve the species, actually, this active species formed after 4 hours. We see this iridium OH nanocluster form along the green boundaries. And because the APT can have this local magnification effect, we can use this density variation of this a single element to notice that there's a green boundary. So therefore, we can see that there is a nanocluster active iridium OH was forming along the green boundary and serving as active sites for the OER. Another example is a study done by Kevin Schreiner from MPIE, and basically he deposits iridium ruthenium thin film on the silicon coupon and then oxidize it. And afterwards, use the synchrotron-based scanning photoinformation microscope to see the oxidation state of this oxide after they form this oxides. And then they use APT to see the conversation. So this is another kind of a multimodal approach to see the pristine state, what is the oxidation state, and what is the conversation on the surface. And recently, my group also trying to push a little bit further. We directly use the APT tips as a nanosize electrode, and we perform the electrochemical testing. And afterwards, we put this APT tips into SPS to see the oxidation state after the OER. And then I use APT to see how the surface oxide form. Again, the beauty part of the APT, and also this part of the artifact, because a single element, we can perfectly resolve the surface facets by using the density variation. So as you see here, we can resolve the oxide thickness formation, oxide different composition in the oxides on different facets. So this is again gives a facet effect, how the formation of the oxide along different facets. So these are the examples, like the first part of the talk, and also these examples. Actually, we measure the specimen in the bulk form to have the electrochemical performance. And this bulk form specimen can be a few hundreds of a micrometer, or even larger, like the centimeter size. However, for the APT and TEM analysis, we really narrow this down to within 100 nanometer regime. So essentially, we oxide something and we look at something really small. So the next part is I'm really trying to wonder whether or not we can link this local activity, this local structural and compositional change. So this is again the EBSD mapping. So what I'm wondering is can I sort of review that what is the activity across different facets, and then I understand the structure and compositional change on these facets. So back to this contact, so this is the beta COH. So if they keep doing the CV cycles on the cobalt facet, so I'm wondering what the species form on different facets and how this influences the OER activity. So in this part of the talk, I will correlate the TEM APT with this correlative EBSC SE-CCM to see the facet effect that beta COH on the OER activity. So what is SE-CCM? This is a scanning electrochemical cell microscopy. Basically, you see the plot on the right-hand side. You have a pipette, and you have the electrolyte going through this pipette. You can measure the current and also voltage, and you have this different droplet cells. I mean, across the sample, you can keep hopping on the sample to different mode of the electrochemical measurement. So essentially, the reaction area is determined by the size of this tip of the pipette. So what I'm doing here is I'm trying to firstly mapping an area with EBSD mapping. I know what is the facets along this area, and then I'm using this hopping mode and trying to measure the current information on different facets. And then I correlate this EBSD mapping with this SE-CCM mapping to understand how the facets influence on the OER current. So I gave you a taste of how the SE-CCM data looks like along at each hopping mode. So you can see this is different numbers of hopping. So this is you have initially you have some of the facets have a huge current change, some has a less amount of current change. Essentially, we speculate what exactly happened during this process. Is at beginning is forming this active species, and once it's formed, the current increment that represents as this contributes this OER activity because the OER takes place and making the current increase. So if we use this information and then correlate this, how there's a current increment at different facets, and then we can plot such a kind of a statistic analysis to give idea how many say different facets have different this current trend basically. As we can see here, the 01 bar 11 has the highest OER current increment, and for the 0001 facet is really have the minimum. So in order to make it simpler, I say this is a red facet and different color, purple and green here. So then I will use the TEM and APT to prepare samples from different facets and in order to see the structure and composition changes. As you see, I select the red and the purple and green facets to prepare the APT and the TEM specimen to see the structure and composition change. And just a reminder, after OER, we have a mixture of a 2+ and 3+ on the surface, basically. And for the TEM sample, for the TEM specimen, and we can see that for the 001, you have the beta COH. I think we already know this is also basically basal plan allows basal plan COH formation. And by doing this, we can see the different growth orientation. And for the CO1012 is allows the formation of 10813 beta COH. So you have a different facets essentially form on the different facets of a cobalt. And interestingly, if we look at this, and because of the growth rate along different facets also different, and we see this a bit of pyramidal planes allows a little bit slow formation of this beta COH. We have a thin layer compared to this basal plane growth of the COH here. And if you zoom out a little bit to looking at a bit of larger area, and we see additional reflection spots from the HRTM images. And if we trying to dig it out what exactly is, and these spots fit very well with beta COH2, which is the 2+ beta hydroxide. So essentially, for the facets, we have a mixture of beta COH and beta COH2. And afterwards, similar thing, I prepared a sample from red, green, purple grains. And this is a different APT data set, and you can see the oxide thickness is also different, which is matches very well with the TEM analysis. As you also know, we can guess this orientation also from the cobalt metric by simply plotting a cobalt 2D density maps, and you see there's a different symmetry, and we can get the orientation of this cobalt. And we can also place a cylinder just directly along the 001 on also bar 12, bar 10, and also the other plane, and trying to only looking at along this plane and what is the hydroxide oxide formed. So if we do this, we can have the local atom maps, and you can see this is the shows the difference of this hydrous layer. And for this, the purple facet has the thinnest hydrous oxide formed. And again, we can use one concentration cylinder to plot the composition profiles and get the ratio of cobalt, oxygen cobalt ratio. And very interestingly is we see that the surface oxygen concentration is different. And for 001, we have a little bit higher oxygen concentration. And for the 02, bar 2, 1 orientation, and this facet, we have a bit of a lower amount of oxygen. So this is what we talk about here is getting a little bit tricky, how we interpret this data. I mean, of course, APT cannot give the oxidation state, but from the SPS and also TEM, we know that there is a mixture of a 2+ and 3+. So essentially, the 2+ is COH2 and 3+ is COOH. And if you're looking at the bond dissociation energy, I'm wondering, and this is something we should do the DFT, or we should do APT analysis of a direct cobalt hydroxide and cobalt oxyhydroxide to see the exact dissociation behavior of this complex hydrous oxide. But if they simply refer to the bond dissociation energy, I was speculating that the OH group maybe doesn't like to dissociate much. So essentially, for the COH, we dissolved the COO and OH, and COH2, there is CO and OH. So essentially, this can give us a different ratio for cobalt, oxygen, and cobalt. So we speculate that in the O1, and this mainly contains COH because of this higher oxygen to cobalt ratio, and for the other facet, this is as a more proportion of this CO hydroxide, and as a mixture of COOH, and have a higher proportion of this hydroxides. So essentially, how this correlate with the activity information. So first of all, let's say I talk about, say, we prepare this microelectrode and we perform the electrochemical testing. We can use it, say, the conventional CV test to have idea of OER activity. But on top of it, if you use the local SECCM and SEM EBSC measurement, we can get the activity at each single facet. And this behaves differently, essentially different facets. This is because we form different facets of this active species, this is beta COH. And also the thickness of the active species is different. And by using the APT and to resolve this different cobalt and oxygen ratio, we resolve that for this 1,0.3 is actually contains more of this hydroxide. So essentially it means this 3 plus is easily to reduce to 2 plus, and this reducibility of this cobalt size is highly important for OER, and this is actually an indicator as a active size for this OER reaction. So this means the high activity of this purple facet is because it's a highly reducibility of this species on the surface. At the same time, if we look at the cobalt oxygen coordinate size, and for the purple facet, it has 3 coordinate, they have a more available size for another oxygen coordination. So this is also more active compared to the other facets. And also, if you look at if they placing this in the slabs exposed to the electrolyte, and the electrolyte is easily to penetrate into the slabs, but for the 001, it was blocked by the basal planes. So this is again the more easier for the electrolyte penetration, the higher activity of the OER. So essentially, we use this combination of the multimodal approach, trying to resolve this local activity difference and to have an idea of why this difference by using APT and TEM. So like I said, is so we have a overall picture.
3 minutes to go.
Yeah, just 30 seconds. Yeah. So like I just said, is we use this multimodal approach to have the enzymal activity and local activity, and combine the SPS, APT, and TEM to have a look at the oxidation state, composition, and structure information, and link this with the activity change. So we really pull out of information from APT to see the local compositional changes, and therefore to understand this local activity difference between this beta COH facets. So last and not least, I want to thank Professor Gangsha for the invitation for this talk. I want to thank the funding agency and also the team who performed the experiment, and also the collaborators to contribute to some part of the result. And thank you for your attention.
Okay, wow. Thank you so much for sharing your amazing research. That was a true demonstration of atomic scale materials characterization, and also really nicely showing how looking at materials from different angles with different gives different perspectives that all can feed into the bigger picture. I think you were fast enough, so we have a few minutes for a couple of questions. The first one I see popping up is from Arun. Arun, please go ahead and ask your question.
Hi, Tom. Can you hear me?
Good morning, Arun. Yeah.
Good morning.
Yes.
Yeah, great talk. So I have 2 related questions. First one is when you actually keep cycling multiple times, I've seen that the surface porosity can keep increasing. So does that interfere with your atom probe analysis, especially for the later cycles? That is the first question. The second question is related that when you do EBSD before the CV cycling, occasionally we have seen that there's a thin carbon coating that you can actually deposit during that. So I was curious whether you saw some indication of carbon species in your atom probe results from the different facets that you were doing after EBSD.
Yeah, I mean, for the CV cycle, it's definitely making the material porous, and cobalt is HCP. And if you do EBSD, etc., is even worse. So to get to the data is really difficult and challenging, and the success rate is not high. And it's true, super porous, and is a super brittle, and is absolutely the case.
Okay.
And I don't know if because we coat the chromium on top of it in order to protect the surface layer, and maybe the chromium somehow can also immerse into this porous region somehow, helps a little bit, and we still can have certain data that like you see this today, but it's absolutely this is a bit of a problematic. The thing we can think about is I mean, now I'm just trying to code the sample and do the conventional lift out. I mean, it's really causing a problem. You can just put a 90-degree and use the other, like making the interface like 90-degree instead of making the 180-degree conventional one, and then the 90-degree will help. And this is I did it for iridium before. This is a CV cycle, like this vertical lift out, and you have the interface. Yeah, and for the carbon deposition, this is the part actually I'm not super know this, and the student performed the EBSD, and I didn't quite pay attention to the carbon deposition on the EBSD mapping, because at the end of the day, we perform the EBSD, and afterwards we putting the microelectrode to the CV test. I mean, whether or not this carbon coating affect the CV, I don't know. I mean, this is maybe not, but at the end of the day, I guess this carbon will kind of dissolve or mixture with this oxide. This is what I'm not super sure about this. Yeah.
Okay. Yeah, and sorry, related. One more related question that I had is like once when you are in solution, you have a certain surface chemistry, but as soon as you take it out for atom probe, right, you have to dry it, and then there's an oxidation. So how are you verifying if the surface chemistry is changing while in solution?
Absolutely.
Yeah.
Absolutely. And this is the most controversial part, and that's why I also bought this VCTM and trying to protect the surface after the summer preparation. This is absolutely problematic. And on top of it is this state, oxygen state, is related to potential and also related to the environment. So this means even if we don't dry this after we get out of the potential, I mean, this is something surface will change, but we're talking about superatomic scale now. But with that APT, we cannot even resolve the difference, to be honest. But I think there's absolutely a problem. And that's why I will use a thermal transfer later on, and to protect the surface as much as like you guys did, Daniel Perret, and you have this transfer device, and then also MPAE, etc. Yeah, I think everyone is on the internet. Yeah. Your microphone is out. Florian, your microphone.
Oh, sorry. Let's thank Professor Lee again. We're running a bit behind schedule. Ivan, may I ask you to post your questions in the chat box, and then we can move on with Gustav Eriksson from Chalmers University of Technology.
Good morning.
I think we have extended breaks. Maybe people can come back if you want to ask more questions to Tom. Because we
sure.
Break, yes.
Yeah, okay. We have some time in the end.
Yeah, when the end of this, afternoon sessions, the first half, and we have a longer break. So if people have the more questions to discuss with Tom, and I think you can.
Okay, sure. Then
I will be around. Yeah, sounds good.
Okay, Gustav, you may share your screen and start your presentation.
Thank you. So I hope you're able to hear me and see my screen by now. My name is Gustav Eriksson, and I'm a PhD student at the Department of Chemistry and Chemical Engineering at Chalmers University of Technology in Gothenburg, Sweden. And I'm happy for the opportunity and thankful to give this presentation entitled Analysis of the Gold Nanoparticles by Embedding in Silica. So this work that we've been carrying out here in our group is motivated and continuation on the previous work that has been done here. Nanoparticle systems, they have been analyzed before using atom probe tomography and various other techniques. But previously in our team, we've been studying and are still attempting to study biomolecules such as proteins by silica embedding. And we've done this in atom probe tomography in a work published a few years back by colleagues of mine, where a sol gel solution containing a pH-adjusted sodium silicate, which gels at the neutral pH into a gel-like structure that can be dried to obtain a solid material. And by adding proteins during this process, we can end up with a solid material containing proteins that are retained in their hydrated state. And we've been attempting to develop this further, but there are some troubles or complications related to this type of material. So one of the challenges is that we don't have an even distribution of the proteins inside this material. It seems like they are, considering the small volume that we analyze in the APT, we need to be a bit lucky to find a protein in this volume. And also we realized that this silicon material has properties that are not very challenging, making it challenging to study in the atom probe. It has poor conductivity, and evaporation field of the material is quite high, making it prone to fracture during analysis. So when developing this further, we wanted to confine a region of interest like this one to a surface. So our solution to do this is to make a film, a silica film on a substrate. So we have a similar water glass solution that can contain, for example, biomolecules, and we can spin coat it on a substrate such as a silicon wafer to end up with a silica film that is 100 to 200 nanometers thick, containing the region of interest, making the material a bit more friendly to analyze. Also, when developing and thinking about this concept, we came up with the idea of anchoring our objects of interest to the substrate to ensure that at this surface we know where, for example, proteins, if we're interested in them, are located. And it was at this point we started to consider the nanoparticle systems, because in order to properly anchor proteins to such a substrate surface, we wanted to have them on some objects that are easily identified, and also allows for better retention of the native structure of, for example, biomolecules. And also we realized that such nanoparticles can be of interest to study themselves, and since the silica matrix can allow for retention of the hydrated state of objects such as these ones, we think that this could be a promising study. So the methods that we've been using in order to synthesize these kind of systems or materials is that we've been working with silicon wafers, and they have a thin chromium film, 10 nanometers in thickness, that is heat treated to give a good adhesion to both the underlying substrate and the silica later on. And this kind of substrate is chemically modified. So I've used a self-assembled monolayer of a linker molecule. This one is mercaptosilane that is placed on the surface, and it will have these thiol groups outwards, so to speak, towards solution or surrounding environment. And when placing these molecules in this monolayer on the surface, it allows for good binding of especially gold nanoparticles to such a substrate or surface. So I've synthesized particles in our lab and been able to place them on the surface so that they are individual particles. They haven't aggregated and they are bound from solution, but they are densely packed. So the distance between the particles is quite low. And this material can be embedded in silica by spin coating a sol-gel solution. And prior to this embedding, there's a possibility for further modifications. So once again, thiol chemistry could be used to place biomolecules on these particles. And this is something that is readily done in many applications. So this could be further developed in that sense. And to characterize the materials that we've been synthesizing, we want to follow this synthesis at the various steps. So we've started by doing SCM of the modified surface prior to the embedding in silica. So here you can see the gold nanoparticle modified surface, and the size distribution of the particles is around 30 nanometers. And when looking at the nearest neighbor distance between particles, the average distance is around 60 nanometers, which is close enough to have a good likelihood of encountering a particle when analyzing, when making an APT specimen from this material. And after silica embedding, I've done TM liftouts according to the normal protocol and been able to study the material once it's embedded in silica. And this is what such a liftout can look like. And it's a lot going on in this image, but we have the silicon substrate at the bottom, which is the silicon wafer that we've been working on. And we have the chromium film, and you can see the effects of the heat treatment here as well. We have the gold nanoparticles, of course, that are placed on this surface. We have our silica film that has been spin coated on the surface. And here on top, we have a sputter coated gold film for some protection and increased conductivity during the FIB-SEM work and the protective platinum coating from the FIB-SEM work. And in the same way that we can make TM lamella liftouts from such a material, we can, of course, prepare APT specimen according to the ordinary FIB-SEM protocol. And finished specimens that are prepared in this way can look something like this. So it looks like APT specimen normally do. And when we use the backscattered electrons to image them, we're able to actually see, for example, here's a gold nanoparticle on the side of such a specimen. And here is our protective sputtered gold coating and the underlying chromium. So we're able to prepare a specimen containing particles in a nice way. Of course, since this region of interest is just below the protective layer and at most like 200 nanometers thick, there's some requirements for the operator to be a bit careful during this, so you don't mill away this region of interest while preparing your specimen. And of course, we interested in analyzing these specimens and see what they look like, and we can end up with something like this. So this is a reconstructed volume of one of the specimens analyzed, and you can see obviously the gold particle that we were able to study here, and surrounding it is actually chromia related species that was evaporating at the same time, and we have the underlying substrate with chromium and oxide related species from the chromia, and further down we will be able to see the silicon substrate. So when looking at these particles, we can, this is another reconstructed volume from a similar specimen from the same type of sample. We're able to partly have a look at in gray the silver ions found in the particles. So silver is often used during particle synthesis to regulate the shape, and one of the strengths of studying particles in APT is of course that we have this good chemical resolution and are able to investigate such things. But also in green we're able to see sodium. So this could be the sodium citrate ligands that are used to stabilize these particles in solution. And this is I think one of the strengths of working with such a silica material, that we could be able to retain such ligands, stabilizing ligands in hydrated states. Yeah, and of course we're able to do the normal investigation and characteristic work, where we can have a look and make cross sections of regions of interest and see if there is any special distribution of specific species, such as the silver ions inside the particles in this case. Yes, in several of most of the specimens that we investigated, we found that the gold nanoparticles, they would appear together with chromia, and we thought a bit about why would this could happen, and we found that the particles ended up early in our specimens as well. And a possible explanation that we're thinking about here is that since this is a very simplified illustration of what the specimen could look like, and we have this silica film at the top, and we believe that the adhesion between this particle and the silica could be quite poor, so that when we start the analysis and apply the voltage, we could have a small fraction where this silica is torn off, and we end up with something looking like this. And this could explain, if we have like sharp regions here, we can have a high localized field where we get evaporation of chromia at the same time as the particle, ending up with this phenomena where it seems like these particles are embedded in the chromia. So there are some conclusions that we can make from this work so far, that this could be a platform for studying these sorts of nanoparticles, and we have a quite high throughput, in the sense that by chemically modifying the surface, we get the particles that are still discrete, but they are packed close enough to have a high likelihood of encountering one when preparing our specimens. And the silica could allow to retain stabilizing ligands or adsorbents in a hydrated state and study them on the nanoparticles. However, we believe that the particle silica adhesion is quite poor, which causes this effect of having our particles appearing early on in the analysis and seeming to be embedded in our underlying substrate almost. And we've encountered challenges when trying to bind thiol-modified proteins or other biomolecules to these particles. So we would need to, of course, further develop these techniques in order to have this as a platform to study not only particles, but other molecules of interest attached to these particles as well. And I would like to thank you for listening and attention, and acknowledge the Swedish Wallenberg foundations that have funded this work. And I'm not sure if we have time for questions, but if you have thoughts or something, you're most welcome to send me an email afterwards.
Thank you very much, Gustav, for sharing the results of your challenging research. I think we may direct the questions to you directly via email or chat message, and try to keep the schedule and move on to the next talk, which will be given by Yuan Yu from RWTH Aachen University in Germany. Yuan Yu, the stage is yours.
Thank you.
In ink and quantum worlds. Welcome. Will you please share your screen? The stage is yours.
Please share my screen now. Hello, can you hear me and also see my screen?
Yes, both okay.
Oh, great. So thank you, Florian. So good morning, everyone, and also good afternoon and good evenings to those who are not in my Zoom. So my name is Ray Shu from Oxford, and my talk today will be about APT investigation on the role of indium in ink-and quantum wells. And this project is in collaboration with Cambridge. So first, let's talk about LEDs. So LEDs are the semiconductors that could emit the protons when the current passing through the material, and the energy gap in the material in the semiconductor would decide the wavelength, or namely the color of the light. So, and because of its wide range of benefits, such as the energy efficiency and so on, it is now it has been like greatly developed in recent decades, as we can see on the right hand left figure here, and especially in luminance efficiency, and also in our daily life, we can often see its application. And despite of its commercially successful rise in those kind of like GaN-based optoelectronics over the recent years, the so-called the green gap issue is remained to unsolved to date. And this term refers to this term refers to the rapid decline in the quantum efficiency for the InGaN-based emitters at longer wavelengths beyond the blue spectrum range, as we can see on the right picture here. That's in the range of green light. The maximum or external quantum efficiency would drop sharply here. So to solve this problem, the researchers now are looking into the origins of the efficiency issue, and people now are focusing on the factors that would affect the radiated and non-radiated free combination process. And so more precisely, it is about the carrier localization and the alloy fluctuations, and the increase in the lattice mismatch reduced strain, and also about the reduction in the material quality with increased indium nitrogen fraction employed to reach longer wavelengths. So, like relates to the intrinsic property of Woodside-C plane heterostructure. A potential strategy to avoid such problem is the application of non-polar bus. So why we are using thin film bus? And if we take a look at the structure here, comparing to that one, we can find that the thin film GaN-based structure, especially in the 001 orientation, it is free from both spontaneous polarization and also the piezoelectric field. And also it has a smaller band gap than the work done fast. So in this way, it is predicted to be more efficient green emitters. So here is the structure of our sample. What we are interested in is this part. And we here have like 5 layers of indium quantum with the GaN barrier in the between. So apart from achieving fast purity during the fabrication process, the 111 samples are the most abundant planar defects. As we can see in this picture here, these defects would like interrupting the ABCD bilayer stacking of the zinc blende fuzz here, which would be bound to affect the quality of the material and further result in a poor performance of the devices. So apart from trying to optimize the fabrication process, and researchers now are also looking into the role of these stacking bolts. And it has been now reported that the stacking bolts in the zinc blende GaN, it's the non-radiative centers, and also it is related to the local electric field. However, its impacts on the ternary alloy composition in the cubic GaN remains to be explored. So to study this, we conducted a series of tests on this sample. So first, here is the cross-sectional image, and this was used to characterize the correlation between the stacking bolts and the variations. So picture here shows an overview of the cross-sectional image of the hydrostructure. We can see that in the picture, the planar stacking bolts are visible here as inclined lines of contrast through the multi-layer, and some of them are highlighted by red arrows. And it shows that like individual stacking bolts and groups of planar defects tend to roughen the growing surface locally, causing the buckling of the indium quantum mills. And the figure here is actually a higher indication originally caused by the blue square here. So we can see more clearly that the composition varies around the stacking bolts. Like and the quantum mills is shown in the red box here. And also this blue rectangle, which contains like 5 layers of quantum mills, and also the part, the APL, and also GaN matrix, it's further analyzed by EDX. So here comes the EDX results. So the region of this picture is exactly mentioned in last slides. So you note that this image here are oriented such that the stacking bolts is running horizontally, and the red arrow here highlights the approximate.
May I interrupt you for a second? Your audio signal is sometimes bad. Do you can you make sure everything is okay with your microphone, or perhaps it's your internet connection, or just double check your microphone if you can.
Yeah, can you hear me clearly? Can you hear me now? Sorry.
Yeah, we can hear you. The signal is just sometimes not very clear.
Okay.
Perhaps switch. One idea might be to just switch off your video to lower the load on the bandwidth.
Okay. And I'll try also restart again.
Okay. Thank you.
Is that better now, or?
Sounds better. We see as we go along. Thank you.
Okay. Sorry about that. So so in this picture, the red arrows here highlights the approximate position of the stacking bolt, and we can see that in the picture A, so within the within the layer, the gallium content dropping around the cycles here. And in the image here, this image shows the indium and aluminum distribution of the region displayed in A. So the quantum will show in green bands and aluminum show in purple. So we can find that both the indium and aluminum contents would increase the loss around the stacking force. Yeah, and as highlighted in those black boxes, and as we want to like quantify the local impact of the stacking force on alloy composition, we thereby like chose 10 regions of in both quantum well and EBL region, and compared to 10 regions away from the stacking fault. The average values are given in the table, and it further proves that the indium and the aluminum content around the stacking fault are like approximately a factor of 2.3 or at 1.9 higher than that of like adjacent alloy material respectively. And because of the so because of the outstanding ability of atom tomography, we here applied APT to further investigate both structural and compositional sides of our sample. So as we can see on the left, that one quantum structures were captured with and it's constant with the same results, that they're not the ideal horizontally and uniformly distributed laminar structure, and we then repeat the experiment under different experimental conditions, and there are multiple sets of experiments capture the quantum world structure, which would demonstrate that the reproducibility of this APT result. And also, if we take a look at comparison of this distribution of each element, we can find that the indium it's likely to be more unevenly distributed throughout the material than that of gallium and nitride. So this map of indium also
shows 3 minutes to go.
Yeah, also shows conclusion, and it can be seen that the density of indium doesn't appear to be exactly the same. So we made extraction of individual quantum wells here, and we can see from the image here that for each quantum well, it has a wavy appearance and it always here, which records stacking force passing through. So to quantify the composition of the material, we made a 1D concentration through the quantum well, roughly perpendicular to each quantum well, and the 1D concentration shows as in this picture. So the quantum well roughly corresponds to this part in the boxes. It can be seen that the indium and the rise in the quantum well, and the gallium shows the opposite. And then we take a look at each quantum well separately. The elements are not evenly distributed in each quantum well either, and I can be seen in the distribution of elements from top view that there's some slightly cut associated, and make the 1D concentration along the side this direction perpendicular to the box, and we can see that the concentration changes with this direction, and nitrogen and indium approximately share the same trend, and gallium shows the opposite. And and they're like kind of the metric is also pronounced due to like chance error, like small amount of data, and we will further look into this issue, and also to see more clearly about the Indian aggregation here. I made a ISO surface of Indian, and as is shown here in the density map, that slightly Indian band distributed parallel to each other in the quantum well layer. And if we look into one part of this, and it's a proxygram, you find that in the center of the band, the Indian are like increasing, and the gallium nitride would show a decreasing trend, which is not the same as we mentioned before, and this is quite interesting, and we'll also continue to look into this issue. So in summary, the quantum well were observed using APT in this study is the twisted ripple structure, and significant enrichment of Indian quantum wells were observed. So our further work is to determine the angle of quantum well ripples and their crystalline orientation, and also optimize the APT-1 conditions as a semiconductor material. So that would be all I would like to cover today. Sorry about that. Yeah, that's the end of my talk. Thank you.
Okay, Ruying, thank you very much. Unfortunately, the audio signal was really bad at times, so sometimes it was really difficult to understand. Maybe you can double check if you're using a microphone or earphones, or move to a place with a faster internet connection.
Okay.
Thank you for the interesting talk, though. If there are any questions, please send Ruying an email or just post it in the chat box. And with this being said, we will move on to our next speaker, Ivan Postuga from Forschungszentrum Jülich in Germany, who will give us new insights into oxidation of alloys with 18-oxygen tracer-assisted atom probe tomography. Ivan, the stage is yours. We'll give you a 3-minute warning in the end.
Yeah, okay, thank you, Florian. Do you hear me well?
Yes, I can hear you very well. Ruying, you may stop sharing your screen, so Ivan can go ahead.
Yeah, okay, so good morning, everyone, or good afternoon, good evening, depending on where you are. I would like first to thank the organizers for giving me the opportunity to present the data, our recent results. And today I will just briefly speak about what we can learn about the oxidation of alloys when we use a tracer-assisted atom probe tomography. So the background for the talk is quite easy and straightforward. So our oxidation or corrosion in alloys, it occurs under many service conditions, increasingly at high temperatures, and causes severe economic losses. So everyone tries to suppress it or to minimize it. And often protective coatings are used for that purpose, but it's not always possible from technological, economical, and other reasons. And a typical way to protect or self-protect the alloys from oxidation is the formation of the surface oxide scales. These are typically alumina or chromia based. They form at their service conditions or at any other conditions. The key requirements for them are no spallation of the surface oxide, so it forms and it protects alloys from further oxidation, slow growth rate, so the alloy does not degrade very quickly, and for high temperature oxidations, it's a high temperature stability, so the oxide scale grows and stays on the alloy, protecting it from further degradation. The effect depends strongly on alloy composition, including minor elements. For example, if you take a pure tungsten, the most refractory metal, and oxidize it at just 1000 degrees C, you will get something looking like this. Very fancy, but not useful. And if you take an alloy which contains chromium and yttrium, you will get much better oxidation resistance, much better material state after the same exposure. Just a nice example how their elements can change the oxidation behavior of the material. And of course, understanding the mechanisms is very crucial for the alloy design. Formation of the surface oxide scales, just to show how they look. If you look at the cross-sectional view of the oxidized alloy, the oxide scale may contain from one layer, it may be complex, containing from different layers, outer scale, inner scale. Sometimes the internal oxidation zone with oxide precipitates is formed. And if you look at the schematics of the alloy oxidation, when we expose it to some oxidizing atmosphere, the alloy starts to oxidize. Partly the oxide scale may grow inward, partly outward. The original alloy surface was somewhere in between. And it's happening due to their mostly diffusion of their either anions, namely oxygen, the inward diffusion toward the oxide surface. This is how the inward growth occurs, and the outward diffusion of the cations to their outer surface of the sample, which produces their outward growth of the alloy. The ionic diffusion goes predominantly along grain boundaries. There are many indirect evidences for that effect, but not directly observed yet. Okay, the last statement is not exactly true, because recently there were several papers devoted to their diffusion of oxygen using isotopic tracers in atom probe, but they mostly deal with either thin film samples or with the initial stages of oxidation, like in their paper from the APT&M, the nice results where they oxidized one of their alloys in their environmental oxidation chamber, but it was the transient initial oxidation stages, which were unfortunately not directly related to their behavior of the bulk material and their bulk oxide scale, which protects the alloy from further oxidation. So we selected for our analysis their iron chromium aluminum based ODS alloy doped with yttria for several reasons, because it's a base for many industrial high temperature alloys. It's alumina former, so no overlaps or nearly no overlaps in APT mass spectrum comes from the use of the O18 isotope tracer. Yttrium is known to segregate at oxide grain boundaries in alumina, which helps to highlight the grain boundary positions in the atom probe datasets. And the alloy grows mainly inward, so the growth is controlled by the oxygen diffusion. We could, of course, use the correlative approach to identify the positions of the oxide grain boundaries in the datasets, as we did in our recent work, but unfortunately, this approach takes quite a lot of time and quite a lot of efforts, and using the yttrium as a marker for the grain boundary position would be a much easier approach. That's why we used that composition. If you look at their oxide scale grown on this alloy, we oxidized it at 1200 degrees C with a two-stage experiment. Our first stage was in the argon with natural oxygen, second stage with argon in the mixture of argon and O18 enriched oxygen. The oxide scale in the cross-section looks like this. We see the bigger columnar part grown from the inwards growth, a small outer part with the original alloy surface somewhere here between these regions. And we used a simple thermogravimetry analysis for the oxidation of the sample, where we oxidized it and measured simultaneously the weight gain proportional actually to the oxide scale thickness versus their exposure time. The first stage was for 4 hours, and it provided us about a half of the thickness of the oxide scale, so the outer part, and the second stage gave us the inner part of the oxide scale. So that was quite convenient for analyzing this later in atom probe. And normally, so we expected to see the O18 at the grain boundaries of the outer scale when it diffuses inward. Typically, methods such as SIMS or SNMS secondary neutral mass spectroscopy is used for analyzing their oxide scale after their formation. And for this alloy, SNMS showed us that, okay, there is enrichment of O18 in the inner part, expected, quite notable level of O18 in the outer part, assumably due to the isotopic exchange, and so on. But we decided to look into different parts with APT, outer scale, inner scale, and the metal oxide interface. But first of all, we decided to test the O18 concentration in the second stage gas because nominally it's 20% of O18 in the total O, but direct measurement was not available. We didn't have a technique for that. So we simply used a bypass trick. We used one-stage oxidation in the same atmosphere and used atom probe for analyzing the oxide scale to test the amount of O18. Mass spectrum looks indeed simple. All peaks can be identified, assigned to certain isotopes. But when I said that there is no overlap, it's not exactly true because there is always a O18 18 Dalton's peak, which may come either from O18 or from water. And it may cause the bias of their bulk composition. So we used their complex ions peaks for the correct ratio of O18 to O16, namely the aluminium O double charged, and with a careful region at 1/10 of the maximum to be sure that we measure the O18 fraction correctly. And in this particular case, we measured that their O18 concentration, the O18 ratio in the second stage gas was a little bit below nominal, namely 18.2 plus minus 0.2%. Check of the electron microstructure before and after exposure showed, okay, there are precipitates of yttria in the alloy matrix, which grow after the exposure. But the most important point for us was the O18 level in this precipitate, in this state and in this state, so before and after exposure. And in both cases, it was quite close to the natural abundance. So we can call these precipitates as compositionally pristine. Nothing changes after the oxidation. After exposure, sample was taken from a deep part of the alloy far from the oxide scale. When we look at their oxide scale in the inner part with APT, we observe very homogeneous distribution of O18. Yttrium decorates grain boundaries, very easy to recognize. Quantitatively, if you look at their composition across the grain boundaries, nothing unusual. Only a grain boundary segregation shows that from the level of the grain boundary axis, that all these grain boundaries are high angle random grain boundaries. And their O18 level in this inner part of the scale is about 16%, which is slightly below their gas, the fraction of O18 in the gas, which indicates the O18 isotopic exchange when the O18 at the second stage runs through their already formed outer oxide scale. If you look at the outer scale here, we expected to see O18 segregation at the grain boundaries, so colocalized with yttrium segregation. What we observed was a little different. Yes, there are grain boundaries where we see the O18 co-segregation with yttrium. But there are also regions which look as quite broad strips up to 50 nanometers in thickness with enriched O18 level and with quite compositionally sharp back interfaces. We used their ionic density to look where these interfaces are grain boundaries. Those which show yttrium segregation, these are indeed grain boundaries, okay, well known from their different evaporation fields of different grains with different orientations, so quite a well-known effect. Interfaces which do not have yttrium segregation show no such features. So these are, as we concluded from their consideration of the ionic densities, were not grain boundaries. All other data sets, they show basically the same behavior, quite broad O18 enriched regions around many grain boundaries. All grain boundaries show O18 enrichments with two clear types, some of them thin as expected, some of them—
Ivan, you have
strips.
3 more minutes.
Yeah, okay. And also in some data sets, we observed such as one and a half dimensional enrichments of their O18 segregations. But okay, that's just a side effect. Compositionally, if we look at these grain boundaries, we observe quite a high level of O18 at them. So not just a normal segregation with a couple of atomic percent of O18, but quite a high level, up to 10% at all grain boundaries and all the same. And if you look compositionally at these regions, at these broad strips, they have the same amount of O18 as the inner scale. So they apparently grew up together with the inner scale, which was quite unexpected, as we thought that alumina formed in the outer scale and that remained after that stable. And if you look in their grain composition, then their oxide level is, O18 level is above the natural abundance. So it indicates the indeed isotopic exchange when O18 runs through the grain boundaries, but that at quite a marginal level. And if you look at the alloy oxide interface, and especially at the internal oxidation zone precipitates, we observed there is quite a high level of O18 in these precipitates, which was absolutely unexpected for us. We expected to see them just as coarsened precipitates from their original alloy, but we have up to 10% atomic percent of O18. And compared to the pristine precipitates in the deep alloy, which showed nearly natural abundance of the O18, this comparison shows that basically, and when recalculated into their O18 fraction, it shows that the concentration of O18 in the inner oxidation zone, in the precipitates and in the inner scale is the same. So it indicates that this is an internal oxidation process. And that's absolutely surprising because yttrium was fully oxidized during alloy production. So there must be no yttrium source to provide this internal oxidation zone, but it happened. And there is no explanation for that for the moment. So to summarize and to highlight some findings, we indeed observed and visualized the oxygen diffusion at their oxide scale grain boundaries, which resulted in the alumina inward growth with their O18 tracer. We observed unexpectedly the broad O18 rich zones at grain boundaries with O18 concentration just below gas, which indicates continuous grain growth and dissolution in alumina, quite an unexpected result. We observed quite a marginal level of their oxygen exchange during grain boundary diffusion, unlike to bulk techniques such as SIMS or SNMS. And we also observed that their internal oxidation proceeds even in the case when there is apparently no source for that from their alloy composition. Thank you for the talk. Thank you for listening. And if there are any questions, I will be glad to answer.
Thank you very much for presenting your results and answering a lot of questions about oxidation, but also raising a few more questions about oxidation. I think we have time for one question. Anybody like to raise their hand? If not, we you can just, oh, there's one question, Christoph Reisold. Please go ahead.
Yeah, many thanks for the talk. I was wondering, do you know anything whether the oxide grain boundaries are stable during the post-oxidation, or is it possible that they still move around? Basically, what you see is the movement of the grain boundary that drags along the yttrium, but basically leaves behind the oxygen 18.
Thanks for the question. We thought, and most of the people who deal with oxidation thought that they must be stable. Okay, we could expect the growth, but in alumina, it was very unlikely. From our results, we assume they're moving, but so as far as I know, so far there is no direct observations or even indirect observations of that grain boundary mobility. So that would be nice to observe that, but technically, I guess this experiment would be quite challenging to carry out.
Yeah. I thought so. I just was wondering whether anything was known already. Thanks.
Okay, let's thank Ivan again. If there is another question, you can just reach out to him directly via email or in the chat box. And with that said, let's welcome our next speaker, Jan Köttgen from RWTH Aachen University again, who will talk about atom probe tomography on battery materials.
Yes, exactly.
Stage is yours. I'll give you a 3-minute warning in the end.
All right, I hope I will get through the 12-minute mark, but I should be fine. Okay, I hope you all can hear me loud and clearly and see my screen. So,
yes, all good.
Nice. So, hello, my name is Jan Köttgen. I'm a student of Oana Kushukaro Mirador, and she cannot attend today, so I have the pleasure to show you our newest results on probing the brittle interface of the metal electrode and solid electrolyte interface in solid-state batteries. So, to start with, I want to first show you the rough principle of a solid-state battery. It consists of a cathode and an anode, as basically every battery, and between a solid electrolyte is placed. And now during the cycling, so the charging and the discharging, the lithium ions move through the electrolyte, and meanwhile, the electrons run through an external circuit. So, but as you can imagine, the worst that could now happen is probably a conducting part that short circuits the cathode and the anode. And this is actually what we start to see after the fabrication already in the SEM. We see the formation and the propagation of dendrites from the electrode to the electrolyte. You see these dendrites as black in the SEM because they have a very high content of lithium. And as lithium has a very low atomic number, it also has a very low scattering power for the electrons, and therefore it appears black. This also means that we can sear the interface between the electrode and the electrolyte very clearly. And this makes the investigation a bit more easier, although we have some obstacles I will mention later. So to understand and prevent this failure mechanism better, we want to investigate the three-dimensional lithium ion transport at this hetero interface. The state of the art is to investigate these grain boundaries using electrochemical impedance spectroscopy. You can see here actually two measurements that are displayed in a Nyquist plot. The red measurement shows a cell where the electrolyte is coated with indium, and the blue measurement shows the blank electrolyte that is contacted with the lithium metal electrodes. And without the coating, the cell has a way larger resistance. So what is the reason for this very strong interface resistance in the cell? Let's have a closer look on that with atom probe experiments. To start with the electrolyte, it is called LiZO. It crystallizes in the garnet structure, and this structure is built out of oxygen polyhedra. And over this interstitial places, the lithium can then move very easily, and this allows a very quick lithium diffusion through this structure. So as you can imagine, this electrolyte is a material that is just designed for allow fast diffusion for lithium when an electric field is applied. So there are already some analogies to the atom probe. So this makes us a few problems. If we have a high base temperature and a high temperature change that is induced by a laser, we observe artificial lithium-rich layers in our reconstruction. And it is understood like this, that at these higher temperatures, the lithium can migrate to the apex of the tip, where it then evaporates at the region of the highest electric field. And then we see whole layers in our reconstruction of lithium. So therefore, we stick to one of the parameters that has a pretty low temperature and temperature change, which is 40 Kelvin and 10 picojoules. Another obstacle we observe is the decrease of lithium content in our tip with the ultra-high storage time. This could be some signs for a delithiation in the ultra-high vacuum. And this effect was already observed already at the MPIE by Kim et al. And to prevent this loss of lithium, we use very gentle milling processes in the FIB and transfer our specimens immediately in the atom probe and also measure them there as fast as possible. The lithium contents we observe then are still lower than we would expect them to be. And this is believed to be caused by a lithium redistribution to the grain boundaries in our samples and the triple junctions. And in both detectors we can use at our SEM, we also can observe this. And as I mentioned already, these black lines come from the high, or are thought to come from a high lithium content at this regions. The accumulation width of these grain boundaries should be at least 10 nanometers or higher, because this is the limited spatial resolution of the SEM. And let's have a look what the atom probe says to that. We could prepare a grain boundary as an atom probe tip. As you see here, this is the final needle. You see clearly the contrast of the grain boundary. And in the atom probe reconstruction, you see then a high concentration of lithium here, which is around 70%, some remaining oxygen, and the other elements are suppressed. Also from these atom probe measurements, we observed that the interface is pretty brittle. That means that this tip basically immediately fractured after we reached the grain boundary. To start with the hetero interface between the lithium and LiZo, let's first have a look on some TEM pictures. In gray and black, you see the grain boundaries of the electrolyte. And if we zoom now on the interface, you see at the blue arrow here, a dendrite that penetrates into the electrolyte. And at the red arrows, we see some lithium-rich filaments that appear 200 to 1000 nanometers away from the interface. And if we then have a look how the hetero interface appears in the atom probe, we observe a very abrupt interface here. There's again a rest of oxygen here in the electrode and around about 5% of zirconium. And on the first glance, you would maybe think now, okay, this could be some contamination while the tips are loaded into the atom probe. But in that case, we would also observe nitrogen, or at least expect it, and this is not the case. So the oxygen and zirconium comes probably from the cell fabrication, from our electrolyte. And actually, there are some publications that could show that the remaining oxygen and zirconium in the electrode causes some of the thermal runaway in the cell. So this is a very abrupt interface, as I said already. Let's have a look how this is the case for the dendrites. We had here a mixed sample of lithium and LiZo, and under that only lithium bulk. And we actually observed already in the SEM some lithium dendrites in the LiZo bulk material. And this is actually contradicting to the common belief that the dendrites only form at the grain boundaries of the sample. And if you then have a look on the atom probe reconstruction, the interfaces at the dendrites here and here are less abrupt than at the hetero interface, but still there's oxygen left and the other elements are suppressed. And to conclude my talk, the atom probe investigations of the interface between the solid electrolyte and the metal anode is possible. Careful attention should be paid in terms of the parameters that are used, either for the sample preparation and the investigation. And we observed a strong segregation of the LiZo electrolyte at the grain boundaries that form so-called complexions. And we observed that lithium dendrites are mainly growing inside the LiZo grain, which actually contradicts the standard belief that they are only forming at the grain boundaries. Therefore, atom probe tomography is a possible tool to map the robustness of a solid-state battery. All right, thank you very much for your attention. I would like our partners from the KIT and the AIST, and do you have any questions? Sorry, I think we can't hear you.
Oh, sorry. I forgot to switch on the mic. I said, thank you, Jan, for this very interesting talk. You were running quite a bit, and I think there's enough time for a quick question. If anybody has, please raise your hand. Okay. Okay, don't see a hand. You can also just send an email. I may have a quick question regarding the lithium. Did you observe any kind of evaporation of the lithium during sample preparation in the FIP under high vacuum conditions, or any sort of loss of lithium?
We have some issues. I think if you mill too fast, actually in the FIP, you sometimes also see some evaporation of the lithium because the tips probably get too hot. We are currently also investigating how this behaves with our cryo stage, but we could not prepare already some experiments for that, and also not of this hetero interface. So yeah, it's not an easy material. You really have to pay attention to that. Yeah.
Okay, thank you very much for sharing these insights. Really great work.
Sure. Thank you.
Okay, so now let's move on to Runchong Wang from Shanghai University, who will talk about the study on the microstructure of second phase in zirconium carbide reinforced iron chromium aluminum alloy.
Yeah, I'm here. I don't have camera, I'm sorry.
Okay, we can hear you loud and clear.
Okay, let's start.
Okay, please go ahead.
Hello everyone, it's a great honor to report my work to you here, and my topic is study on the microstructure of second phase in the in zirconium carbide reinforced ferrochrome aluminum. As a colliding material is the first barrier for reactor safety. It works in high temperature, high pressure, strong corrosion environment, and exposed to fast neutron element irradiation field. The working condition is extremely bad, so the cladding material must obtain very high performance to adapt it. The traditional cladding material, the zirconium alloy, will react with steam and produce hydrogen and release heat. This can lead to hydrogen explosion, and this is the reason of Fukushima accident in 2011. Therefore, it is necessary to find a new cladding material to replace the zirconium alloy. Ferrochrome aluminum is one of the most promising candidate materials. Ferrochrome aluminum has so many advantages to be a good cladding material, such as good corrosion resistance, good high temperature oxidation resistance, and it can avoid the hydrogen explosion. But it also has some many disadvantages that we can't ignore. For example, it is easy to generate a lot of bad phases like alpha prime phase in work condition, and its neutron absorption cross section is much higher, about 10 times than zirconium alloy. So ferrochrome aluminum needs better performance to overcome its disadvantages. For the better performance, researchers took various methods. For example, Goran team added yttrium oxide into ferrochrome aluminum to prepare ODS alloys. But compared with the traditional ferrochrome ODS alloy, the addition of aluminum makes a lot of large-sized yttrium aluminum oxides form in material. This is a bad phase for properties, so this idea is not perfect. Gossov team added titanium carbide into ferrochrome aluminum and make the grain size smaller. And all of these strengthening phase keep stable in high temperature condition. So we think this is a good idea. Now, so the effect of titanium carbide is excellent. So about zirconium carbide, because compared with titanium carbide, zirconium carbide has higher hardness, higher melting point, and lower neutron absorption cross section. So zirconium carbide is very feasible in reinforcement. Wang Hui added zirconium carbide to the alloy, and it can obviously refine the grain and improve the hardness of materials. The research has confirmed the feasibility of the zirconium carbide reinforced ferrochrome aluminum, but research in strengthening mechanism is not comprehensive enough, such as the rule of the second phase in material. So we will focus on the observation and the research of the second phase in the alloy. We prepared these samples by ball milling and SPS technology. The addition amount of zirconium carbide is 0.5 mass percentage. We use TM and APT to characterize the microstructure of materials. We obtained TM results and found that the grain were refined with a size of about 200 nanometers. We can also find that there are a large number of dispersed particles with different sizes in the materials, which exist at grain boundary as well as in the grain. These four figures on the right are the EDS results of the area in the grain wireframe. We can find the zirconium and carbon are segregated at the same location, while aluminum and oxygen are segregated at the same location. It indicates that the zirconium carbide and the alumina generated in the material. Through EDS results, we have marked several typical zirconium carbide and alumina in Figure 1. The contrast of zirconium carbide is low, while the contrast of alumina is high. We can find that some zirconium carbide and alumina positions are adjacent, and we have calculated the size and density of zirconium carbide and aluminum. I'm sorry, I hear some music. Go on. Zirconium carbide is larger than aluminum, but less in quantity, and most zirconium sizes are less than 50 nanometers, indicating that zirconium carbide is dissolved. We observed the pink wireframe area with high resolution. Here. and found that the mismatch between the zirconium carbide and the matrix was about 20.7%, and obvious more fringes were found, indicating that they were incoherent. This leads to high interface energy, which is easy to lead crossing of second phase. For example, this alumina beside zirconium is larger than this single alumina. And next we select this blue wire frame area for a high resolution observation. Here, this is a small single alumina particle. It is found that the mismatch between alumina and the matrix is about 1.9%, and there are parallel planes indicating that the alumina and the matrix are coherent. Meanwhile, it was found that there is a smaller precipitate adjacent to this alumina, and the FTT result showed that its structure was similar to this alumina. From this TM, we can also find a large number of dispersed phases are pinned at this location, and there are a large number of smaller black spots distributed in the material. We speculate that there are other small dispersed phases in the material, so we will use APT to research them deeper further. We use APT to obtain the distribution of different elements in the samples. We can find that the segregation position of carbon, zirconium, nitrogen, and molybdenum are the same, while the segregations of aluminum and oxygen are the same, indicating that there are zirconium, molybdenum, carbonitride, and alumina generated in the material. We can also find that the position of these two precipitates are adjacent. According to the results, we speculate that this binary composite second phase, this is formed in the materials. These APT results correspond to our sublocation in TM observation. The size and the density of various dispersed phases in the material are listed in this table. We can find this binary composed phase is the smallest and its quantity is largest. According to the comparate results, the formation of a large number of dispersed phases will consume oxygen and nitrogen in material, which reduce their enrichment at the grain boundary, avoids the occurrence of continuous large-sized oxide and nitrides at the grain boundary, purify the grain boundary and improve its strength.
Sorry, we hear some sound. If there's maybe somebody not muted, could you please switch off your microphone? Thank you.
Because the dispersed phase can be used as a trap to absorb defects, and the grain boundary with good performance can provide self-healing ability for materials. So a large number of fine dispersed phases and pure high strength grain boundaries in the materials can absorb irradiation defects, which can significantly improve the irradiation resistance. And so far, we have completed observation of microstructure of zirconium carbide reinforced ferrochrome aluminum, especially the second phase, and made relevant speculation according to the results. Later, we will further confirm our speculation through other experiment, and series. There are conclusions of this talk, and we list here. That's all my work. Thanks for your listening. Yeah, it's finished.
Okay, Runchong, thank you very much for your interesting talk. Also, you kept the time very nicely. Thank you for that. We still can hear some sound. That might be either the admin having some background sound, or I don't know if some people might be in the background of you, Runchong. Anyway, we have time for a question. If anybody has a question for Runchong, please go ahead and raise your hand. Okay, cannot see a hand. Okay, with that, let's conclude this afternoon session, and let's thank all the speakers again for their wonderful talks and showing us how we can use atom probe tomography and many other techniques to understand materials better and find new things. One remark again, the session break today will be extended until 15:30. So it will start 10 minutes later, and that will push the whole afternoon schedule back by 10 minutes. As indicated earlier, now if there are some additional questions, I assume the speakers are still sticking around, and you could just start a discussion and maybe raise any sort of issue or questions that you had previously and there was no time to answer. Please go ahead. Thank you very much.
close your eyes, what do you see? Do you see yourself, the path in front of you, the next step? Do you see your ambition, the cutting-edge approach that opens new dimensions in medicine, the biggest miniaturization that lays the foundation for the digital revolution, the holistic perspective that transforms humanity for good, the progressive vision that changes everything, the way you see the world, the way you capture moments, the way you transcend knowledge, the way you define precision and productivity, the way you live, move, love, heal, think, are. Open your eyes. Can you see it? Together, we are challenging the limits of imagination. For those who see beyond. Zeiss. Seeing beyond.
Nanjing, the capital of Jiangsu province, is an ancient capital of the Six Dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan scenic area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of one university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 project, a member of 985 innovation platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. The university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Programming Contest. NJUST vigorously promotes the process of internationalization and has established close cooperation with more than 200 famous universities and research institutions abroad. With joint efforts, NJUST has established international cooperative bases such as Herbert Glader Institute of Nanoscience with KIT, Sino-French Engineer Institute with the University of Lorraine, Technology Innovation Support Center with the World Intellectual Property Organization, to carry out cultural exchanges and promote mutual understanding among civilizations. The university has set up research centers on the Kingdom of Saudi Arabia, the Republic of Belarus, Central and Eastern Europe. Stepping into NJUST campus, there is strong academic atmosphere where elites and masters work side by side. Here stand the verdant and upright forest, the elegant Zixia Lake. Students embrace the vibrant campus life. Here, the pulse of Chinese history and culture can be touched. Students experience the speed of development of modern China. On the pursuit of truth and innovation, steps never stop. Explore the world of new knowledge and meet the bright future at NJUST.
Sound check. Can you hear me? Hello. 1 2 1 2.
We can hear you.
Oh, thank you. I was about to cry. Thanks a lot. Well, we just need the first speaker to arrive. We had to shift because he's giving a lecture until about now. And then he has to run into his office and hopefully not trip and fall and break his leg and and then give a talk. So should take another minute or two. Is this better now? Like, can you hear me better? Because the admin was telling me that I was a bit low.
I think that sounds fine.
That's fine. Okay, thanks, Martin. It's maybe my beautiful voice that was not coming across as it should have. And no, I'm not going to start singing. Thank you. François, can you test your microphone, please, just to make sure?
Test. Can you hear me?
Test. Oui.
I'm on the Wi-Fi of the university, so I hope it will work.
I hope so too. Otherwise, I will just sing in the in the meantime. Please share your slides so we can make sure that we attract the massive crowd that, you know, as big a crowd as we can.
Yeah, we'll do that. So share your screen. Yeah. Where's the button? Yeah. So here. If I do that here, okay. If I make it full screen, does it work?
No.
Yeah. Okay. Okay.
Yes, it does work. Yes, it does work. It's well, beautiful is a you know, it's a matter of taste, I guess. So we just wait another 3 minutes or 2 minutes, and then I will give an introduction. And
that's perfect.
And so just to be clear, so your talk is supposed to be about a 30-minute slot. So after maybe 20 minutes, I'll tell you 5 minutes, and I'll give you a 5 minutes warning, and then try to be sharp on time at 25 minutes to allow for some time for questions. Please,
thank you.
Mr. President.
If you are too rude, I fire you.
Yeah, okay. Well, you know, I don't mind stepping down, so maybe I should do that. I'm kidding. Right, so I will time you, and so let's wait another minute, and then I mean, Claudia is suggesting that I start singing. I don't think it's going to work, Claudia.
No,
sorry,
it will not work.
First, I only know stupid songs, and second, my
especially
voice
when
not very good.
When we are at work at 2 o'clock in the morning.
Yes,
your voice is not very clear.
No, so I can ask my daughter to come and sing for you guys. Maybe that could work.
I don't have my euphonium with me, so I can't play it.
And the dog's asleep, so she won't be singing for you guys either. So,
so
right,
people will all right if you show your dog.
Sure.
If you have a
right,
cat, it's better. It's better with a cat.
I don't have a cat. I'm allergic to cats. Anyway, enough about my life. Let's get started with the introduction. So it's my pleasure to introduce Professor François Virpillot, who is the co-lead of the instrumentation group at the Groupe de Physique des Matériaux in the University of Rouen in France, where the sun always shines and it never rains. François did his PhD also in Rouen. He grew up not so far from Rouen, and then he was a Marie Curie Fellow at the University of Oxford for about a year. François' work spans a very broad range of theoretical and experimental work and development work around the atom probe. He's very well known for all of the simulation work that he's been doing, but also the forays into understanding better the theory of field evaporation and laser matter interaction in the laser pulsed atom probe. His contributions are many, and so today he's going to talk to us about removing degeneracy of hydrogen signal in the atom probe for aluminum-based materials. And so I guess, François, the stage is yours. You can get started, and as I said, at about 20 minutes, I will just give you a quick shout.
Okay, thank you, Baptiste, for this very nice introduction. Today I will talk of this subject. Is it possible to remove degeneracy of hydrogen, blah, 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 in aluminum-based material? But it's mainly the work of my ex-PhD student, Loïc Rousseau. He did a very, very nice work on this subject. So I wanted to share it to you because he left the academia. He's now in industry. It's not really industry, but he's no more in academia. So I will try to do my best with the subject of my PhD. To begin with, here, sheet, here. Can you see the slide? It's okay. So we are interested in aluminum alloy. So here you've got an example of a mass spectrum from aluminum alloy, which is aluminum, magnesium, silicium alloy, where you've got nice precipitate of lithium precipitates in the material that you can see in red. And in these materials, you always have some hydrogen atoms that can be seen in green. But the problem is this hydrogen is probably due to contamination. Is there any hydrogen in your material? It's complicated to know because hydrogens come at the same position in the mass spectrum. So is it possible to know where come from the hydrogen, which means you've got a tip, you've got several solution possibility. Hydrogen comes from the atmosphere, it's a contamination, or it can be also on the surface of the material and diffuse on the surface of the material before when you field evaporate the tip. But it can be also inside the material, and this subject is really interesting nowadays. We have seen with the block lecture that hydrogen is quite a hot topic. We can also be interested in the mass spectrum, saying, you've got something in the mass spectrum. Is there any hydride somewhere? It's complicated. So if you come back to the mass spectrum here, if you have a close zoom on the hydrogen peak, as you probably you have seen it in the presentation of the Miller Award, there was a presentation talking about that. In voltage pulse atom probe, I would say voltage pulse atom probe with no reflectron, you see that the hydrogen peak is strange. You've got a sort of double peak, a peak with a hump. So is it possible to have any information of this peak? Also, we observe some strange shape in the mass spectrum of aluminium. So is this bumpy shape hydrides? So it's a question that was raised by Frédéric de Guezet a long time ago, and he supposed it was due to dissociation of neutral in the emission of hydrides. So to understand this we have to know where come from the shape of the. So we've come back to the basic. You've got your tip. You apply voltage. It field evaporate due to the field, and you apply voltage pulse to field evaporate your tip. So it gives you impact, and you calculate the mass over charge ratio with the time of flight. And what we know in voltage pulse atom probe without any computation device, you've got tails for your peaks that are due, what we say, to energy deficit. The ion does not acquire the good energy, and you make this mistake for this atom in this tail. We know that well because if you use an energy reflectron, it compensates for this energy problem, and you get back to very sharp peak, and you are happy because your peaks are very sharp. But in fact, you've got information in this tail that we can use to evaluate some properties of your material. To understand that, you have to go back on the physical principle of field evaporation and look at what is this process. You know, when you have an atom at its surface, it's confined in a potential well, and due to the application of the field, you have an energy barrier for field evaporation that reduces as a function of the field. So it was calculated in DFT. There is a clear mechanism where you can use the pointer, this thing, yeah. You can see there is a linear relationship of the height of the energy barrier as a function of the field. For this field, you've got field evaporation, and here you've got an energy barrier of a fraction of EV. It can be measured experimentally. It's quite cumbersome, but it can be measured. And you see that this barrier depends on the material. And so when you look at field evaporation, you have information about the nature and the neighbor of atoms, since these constants, which are C, are linked to how the atoms is linked to the surface. And if you add, you do voltage pulse atom probe, what you do is simply you put a DC voltage at the regions where the energy barrier is high. So when it's high, it's impossible at 50 Kelvin to field evaporate. It becomes too high for thermal desorption. And on your pulse, you reach the field evaporation and the energy barrier is 0. So it's quite easy to field evaporate. So with the voltage pulse, you simply explore these regions of your energy barrier as a function of the field. So the voltage pulse explores these regions, and the shape of the peak is induced by this variation. To go further, if you look now physically on what you do, when you apply a voltage pulse that we mimic with a Gaussian, it's not really a Gaussian, but we can mimic with a Gaussian, you get most of your ions are evaporating at the top, and some ions are evaporated not at the top, so it means they've got energy deficit. And this energy deficit here can go from 0 to 20% of the total energy. When you calculate the mass, you use this equation, and since you do a linear approximation on the real energy you have, in fact, the mass is shifted as a function of the energy deficit. So your shift in mass is simply your shift in energy. Yeah. Yep. So your mass peak is, I will remove. Your mass peak is simply the traduction of how varies the energy barrier as a function of the energy deficit. And you have this information which is inside your mass spectrum. In fact, if you look carefully, the calculation is a little bit more complicated, but because you have to take into account the real shape of the voltage pulse analytically. So we've got a solution which is analytical that gives you this shape, which looks like the experimental one. And what is interesting is that this slope there in the variation of the quantity of atom as a function of the mass is simply relative to the parameter C divided by KT that you can find. So you can find experimentally this parameter as a function of your parameter. And if you change, for example, the base temperature, you see the slope changing because here T is simply changing. So it works quite well, this explanation. So now if you've got a material composed of different phases, so you can have the same elements. Here you've got silver in the material, so some silver in the precipitate, some silver in the matrix, aluminum silver, but you can see the mass peak are clearly different. Even if you have the same voltage, the mass peak are different, which means the energy barrier can be retrieved. You can know where come from the atom in the material. You can see, localize where come from the atoms in the material, even if it's the same species. So is it possible to use this for hydrogen, which is our wheel today? In fact, it's a little bit more complicated because hydrogen is very fast. And you have to take into account the dynamic effect. If you have a light element, such hydrogen, you've got a speed which is very fast, and then your ion is submitted to different dynamic effect during the flight. And because you cross an acceleration zone and a deceleration zone, and your ion is sufficiently fast to cross these zones where the pulse change because the pulse is only 2 nanoseconds. You have to take into account this effect, but with a simulation, we can retrieve this effect. It's what was done by Loïc Rousseau, for example, and you can see that the dynamic effects are very strong for light elements, and for hydrogen, it's quite strong. And for aluminum, it's close to perfect. You only have a small shift in total energy that can be acquired due to dynamic effect, but for hydrogen, it's quite massive, the variation of amplitude. But there is also an effect, the maximum is not situated at the same position, so it will change the shape of the peak. But we can simulate it. Here, an example with hydrogen, taking the same parameter, energetic parameter for hydrogen and aluminum. It's not true, but it's for the simulation. And you can see the peak here clearly different between aluminum and hydrogen. Okay, but we can have more information. Indeed, if you now have multiple events, for example, you evaporate an aluminum and an hydrogen at the same time, then you will have the mass spectrum for the aluminum, which is collected at the same time as the mass spectrum of the hydrogen, and you can correlate both. You do the successor diagram. But in the successor diagram, you've got a correlation since they started at the same time. But because the dynamic effects are not the same, you've got a shape here which is clearly dependent of the moment where the ion have been field evaporated. And you can know where the pair of ions have been field evaporated, if it is before or after the pulse. So it's a clear indicator of what happens on your surface. This effect was shown very interestingly by Katnagadou and co-workers when they put some gas atom inside the chamber to do film, and you've got here helium and neons, and you've got co-evaporation from the surface of helium and neon. But since helium and neon evaporate at the DC voltage, you've got a trace in the core evaporation diagram for multi-heats that simply show you the variation of the energy and the variation of the pulse you apply on your tip. And you can clearly see the loop that I showed you in my graph, which is there, but you can see also all the non-perfect effects of your voltage pulse that is applied on the tip, because the real voltage is more something like that. So you've got ripple, which is ringing, which is due to how the pulse is transmitted to the tip. So, and we have this also when you evaporate material, except you only look at the top of the pulse. But here, if you've got iron-boron silicon atom alloy, you've got this shape. You have the maximum of impact, which is at the top of the pulse, and you know where the pair are emitted. If you've got boron-boron, you can also see this thing. It can be simulated very carefully, very precisely. Now, let's come back to our aluminum-based alloy and look at our hydrogen peak. And let's try to look at in the Saxe diagram. In the Saxe diagram, it's quite complex. We can recognize some track that are due to dissociation, very interesting dissociation, but we are not interested in this subject today. You also have these strange things here. This is simply the trace of the ripple. I don't know why for this peak you see ripples, but you will see. But we will be interested on hydrogen, these peaks which are in this green square. So in this green square, I make a zoom to see the peak, and you can see that the mass spectrum for the multiple are exactly the same as the mass spectrum for all the atoms. It's because hydrogen atoms are in fact evaporated mostly in multi-heat events. So hydrogen is here the consequence of the evaporation of several elements from the surface. But now if we take a look on the Saxe diagram with a zoom on the hydrogen and the correlation hydrogen-aluminum, you can see that you've got a very nicely defined loop. You've got two loops for the two species. You've got anhydride aluminum plus hydrogen that evaporate from the tip, and also LH plus hydrogen that evaporate from the tip, that are convoluted. But you can see the maximum of the pulse just there. But what is really interesting, very strange, is that the maximum of impact appears here before the maximum of the pulse. You've got an energy deficit which is quite important, and a maximum which is shifted compared to the maximum of the peak. So it corresponds to a difference in time of about 100, 200 picoseconds, something like that. But it's not the difference in time which is interesting, the difference in energy which is shown in this diagram. Also, if you project your mass spectrum for this heat, here you find the hydrogen peak. But if you project this for the aluminum, you've got your gray signals there, and it forms a big hump. And you can recognize the humps that you add on aluminum. Here, it means the signal that you have there, it's aluminum, it's not an hydride, because it's an aluminum atom that has been detected. And it's an aluminum here and a little bit of hydride which is there. So you've got both aluminum and aluminum plus hydrogen in this region. And it says that here you've got some atoms that are linked to the multiple emission of aluminum plus hydrogen. So why the maximum is situated before the maximum of the pulse? So to understand that, we did a simple model. So it's an analytical model to understand that. We suppose that the hydrogen comes from the contamination. So it means we've got hydrogen on the atmosphere that can adsorb on the surface. And since you've got a reservoir, a huge amount of hydrogen in the atmosphere, you have a probability for hydrogen to adsorb at the tip surface. So you've got a constant flux of adsorption at the tip surface. But you apply a DC voltage So it means you have a constant evaporation of hydrogen at the tip surface, hydride at the tip surface, because it's hydride in this case. And when you've got this plateau on the surface, you've got an equilibrium. You've got as much emission than absorption, which make you a level of hydrogen which is constant. And when you apply voltage pulse, you evaporate this reservoir very abruptly here, because you use this equation, which is simply the same equation of field evaporation, except we have to introduce a constant for the evaporation, which is a bit lower than the constant you use for aluminium. It's not 0.5 EV, it's 0.2 EV. And when you do that, you see that the probability is so high that you deplete completely your reservoir of hydrogen at the tip surface, and you evaporate all your hydrogen before the top of the pulse. And here there's no more hydrogen at the tip surface, so there's no signal. And after, it takes a long time for the tip to recover between two pulses, a long time compared to the time of field evaporation. It gives you signals here, which is maximum before the max of the pulse. So you can tune a little bit the parameter in terms of absorption and field evaporation constant. So we've got a couple of parameters that works. It doesn't mean it is exactly the good one, but it explains well empirically the phenomenon. And not that you can have a different track there for different kind of hydrides, but it works the same. So when you change the temperature on your sample, so we did some tests on some pure aluminum specimen, and you can see that it appears essentially at low temperatures, because it probably at high temperature, your probability to absorb or your field evaporation at DC voltage is too high, so it doesn't give you a reservoir, enough reservoir of hydrogen at the tip surface. And it is the same whatever the crystallographic orientation. Now, let's come back to our alloy and look at where come from atom from the peak and atom from the big second peak. The second peak is air contamination. We know it's contamination. In the red peak, we can probably have contamination, but also probably hydrogen from inside the material. And if you localize both, you see the map is different. You've got more red atoms inside particles. So the effect is not strong in this alloy, but you can see some impact. And you can also see that here the amount of contamination is lower on the pole center for these cases, and it's here a bit higher. So probably there's still some contamination in this region. But on this alloy is not very strong, but we found another case where it was really interesting. It's the same alloy, but we've got precipitate of aluminum zirconium. So the zirconium is a real pump for hydrogen. So it interacts a lot with hydrogen. And if you do the same, you identify hydrogen that come from the first peak, the maximum of the pulse, and hydrogen from the hump, so contamination. The map are clearly different, which means here it's contamination. And here, probably the hydrogens are really inside your aluminum zirconium precipitates. So it seems to be a way to evaluate hydrogen from the contamination, at least remove a lot of contamination that come from in the mass spectrum. So to summarize, we provide an indirect means to discriminate hydrogen impurities or contamination. It seems that the contamination of hydrogen molecule change the field behavior of aluminum atoms. And you've got a weak adhesion of these molecules at the tip surface, because this is a parameter you have to put in your model to mimic the mass spectrum. And we see that it is really interesting to use a strike flight path atom probe, because it gives you additional information to uniquely your mass over charge ratio. It's not visible with reflecton, or hardly visible with reflecton. in reflectron, you could probably see the effect, but since the energy variation are completely compressed, it will be more complicated. It's also impossible to do the same in laser pulse. It's only for voltage pulse atom probe, and we also have to be careful because it's complicated process. But you've got additional information. So okay. So I finished my talk. So I'm ready to have any question if necessary.
Thanks, François. It was beautiful work. Are there any questions from the audience? If so, just raise your hand and I will give you, yes, Christophe, please.
No surprise that I have questions. Fantastic, François. One thing that I don't really understand, I mean, you do see that there is hydrogen that has this smaller C parameter on the surface. It's not entirely clear to me whether this allows you to really distinguish whether the hydrogen was there on the surface beforehand or not, or whether this is just a different type of configuration, in particular in the case of zirconium, where simply this sort of say light evaporation size is not present. Can you comment on sort of say how conclusive this is for?
The comment that I had, we see here, because there is a shifted amp, a dynamic effect that cannot be observed if your hydrogen is inside the material, because it's due to the fact that you remove all the hydrogen from the surface. If you've got hydrogen inside the material, your hydrogen will be inside, will not be field evaporated. It's only when it will go at the tip surface that it will be field evaporated. So it's not exactly the same process. You don't have an increase of the concentration of the hydrogen between two pulses if your hydrogen is inside the material. It's only because you've got this reservoir of hydrogen outside that can stick on the surface that you can see this hump and this shift in hydrogen. After, it's possible that the hydrogen which is inside the material have this weak adhesion. Also, it will give you the same physics, but the process, the dynamic process is different because of the way it arrives on the tip surface. So it's only because of dynamic effect that you can see that. A dynamic effect in terms of the thermodynamic process on the surface.
Yes, Hans-Olof, it's nice to see you, please. You are muted. You are muted. You need to unmute yourself.
Thank you. I just wonder, how do you think hydrogen resides on the surface? Do you think it's dissociated, so it's sort of a chemisorption of a single atoms, or is it more physisorption that you have a molecule sitting there on top?
I think we first have a molecule that arrive on the tip surface, and we see all kind of hydrides at the end. You see LH2, LH, even LH3, I think. So and the adhesion of your molecule is weak. So I'm not a specialist of what happened exactly on the surface, but it's a complex process of the molecule doing some link on the surface on the aluminum, probably physically something physically adsorbed, and it's weak, but not extremely weak, because 0.2 EV is still it's still you know.
You know, on noble metals, you very seldom see, for example, silver H. You see always silver H2 and gold H2 and so on. But on more reactive materials like iron, cobalt, and that sort of thing, nickel, you mostly see NiH and so on. So maybe there is a difference on the state of hydrogen on the surface.
So I've got some colleagues in Caen that are specialists of this kind of thing. I asked them if it was possible to have more details of the physics of what happened on the surface.
Yeah. But this effect must also affect your analysis of aluminium, because you constantly lose a little bit of aluminium between pulses, don't you?
Yeah. Exactly.
Yeah. Mm.
You're right.
Thank you.
Thanks, Ansorov. There was another hand raised, but I think it's no longer raised. There's a question from the chat. So how can you exclude that similar effects can be observed in laser mode?
How can I exclude that? We can't see it in laser mode because the variation of the fact that you use a voltage pulse simply enlarge all energetic effects. So you can see things that you can't see at laser mode, where you have all at DC voltage. Probably you've got the same kind of process at the surface, but you can't see it on the mass spectrum. It's the question you cannot identify in laser mode your two channel of field evaporation at the surface, because there's no amplification in energy.
Yeah, the energy deficits would be too low, right?
Yeah.
Are there any other questions? If not, then oh yes, Lee Stevenson.
Yes, sorry,
It's not a
my daughter was calling in the background, but I thought I just had to go, so I lowered my hand. But great talk. I caught some of it, not all of it, because of the time. My question, Francois, is do you think that the tip could be conditioned in such a way that you could deplete the reservoir of hydrogen with perhaps a small pulse before the main pulse, and so then take the hydrogen away from being available for this multi-evaporation, and so thereby get rid of the artifacts completely? I mean, can we use that dip in the hydrogen reservoir that you described to our benefit somehow?
But I thought of that. It's probably possible, but since we evaporate also aluminium with your hydrogen, it will also remove some atom from the surface. You will remove your peak, but you will also lose some atoms doing that.
Okay.
You see what I mean? But yes, I think probably it's possible also to, I don't know, use a weak voltage pulse or a laser pulse before applying your big voltage pulse to deplete your surface with hydrogen and have a clear mass spectrum. But yeah, why not?
I mean, that might get rid of some of the internal hydrogen as well. So I don't think it's like
yes, also yes, you're right.
Yeah. I don't think that idea is inherently foolproof. You know, I would have to be played with some.
I need to catch you. I need to catch you to stay on time. Maybe you guys can take it over in the chat. So Francois, can you stop sharing, please? And I would like to thank you again for the presentation. And there were a lot of food for thoughts in there. And yeah, thank you for giving the talk.
How do you stop yeah.
Well, if you don't do it, I'll do it for you. So the next talk is going to be given by Shalini. Shalini, do you want to share your slides? So thanks again, Francois. And discussion can be hosted in the chat. It's no problem. So Shalini is working also at the Max Planck Institute for Eisenforschung, like myself. She works closely with Christoph, who just asked quite clever questions, and with Shyam and Jörg and Felipe, and she's going to be talking to us about computation of chemical contrast in field area microscopy. Shalini, the stage is yours. You have to unmute yourself first. You have to unmute.
Oh, thanks. Thank you so much, Bat, for a nice introduction. So hello, everyone. My name is Shalini Bhatt, as Brett told, that I'm a PhD student at Max Planck Institute for Forschung. And today I would like to give you the talk on the accurate computation of chemical contrast in field ion microscopy. So I hope that everyone here hear this term of field ion microscopy, but let me give you the introduction of field ion microscopy. So you are able to see my screen, right?
Yes, but we're still on
and the next slide.
No, it's still the first initial slide.
Oh, I'm sorry for that.
That's okay. It happens. Do you have multiple screens at the moment? Are you sharing your?
Yeah.
Yes.
Now it works.
Oh, good.
Thanks.
Thank you.
Yeah, it works. So yeah, so the field ion microscopy was the first microscopy technique to image the individual atoms and for the metal surface and with atomic spatial resolution. So what happens if we apply, let me the point. Yeah. So when the imaging gas is introduced in the vicinity of this sharp tipped needle, so the gas atoms and the high electric field of like 10⁻10 volts per meter is applied. So the gas atoms, they ionized and they accelerate away from the in the direction of the electric field and away from this sharp needle and hit the 2D screen, right? And on the output you see there's a film image. And some are the light green spots, black, and some are the green. So this is what the chemical contrast we say in the film. And this chemical contrast is due to the tunneling. So by tunneling, if you focus on the left of this slide, so by tunneling, I mean the tunneling of the outer electrons from the outer shell of the gas atom, and which tunnels from the vacuum towards the surface. And when the high electric field is applied, so basically the high electric field, it polarizes the gas atom. And what we get is the tunneling of this electron from the outer shell towards the empty available states of the metal surface. And this phenomena is equivalent to the scanning tunneling microscope, for which the Tarsav-Hammond approximation is already known, so that we can estimate this tunneling probability. That explains that the tunneling current is basically proportional to the density of states. So, and these parameters that look density of states, wave functions, and energy eigenvalue, these what we can compute from the DFT. And this is what I'm doing in my work, right? So this Tarsav-Hammond approximation, using this approximation, we can estimate the chemical contrast. So on the right, if you see that I have computed the film simulation, film DFT simulations for the case of the tantalum and nickel, and computed the partial density of states away from the surface, starting from the first, let's say, take the first ionization energy level for the neon gas atom. And so we can see that it's a bright imaging contrast that comes from, of course, from the tantalum. And so the first plot shows for the first slightly away from the surface order of like 2 angstrom, and then we go to the another, let's say if I consider the 15 electron volts of ionization energy level of the gas atom, then we see the another contrast. So it's clear that TH approximation very well explains the chemical contrast, but this was not that we are looking for. This does not explain the real challenges of this DFT simulations, which comes here. So the challenge in the, so this is the partial density of states at the level, if I go little far from the surface, like 20 electron volts. So you see it's completely noisy. And this is the, so here the accuracy of the DFT wave functions is insufficient. So what happened basically when the high electric field is applied, so if we see this on the log scale, so that when the high electric field is applied, so it leads to the faster decaying of the wave function. So it means that the decaying wave function, they somehow turns into the regime of the noise. So there was a need to do the extrapolation of this wave function. And so one has to go more deeper in the vacuum and look for an algorithm that works at the local scale, so that we can work on this film noise problem. So until now I have addressed you this, okay, the computational challenge in the film computing the chemical contrast for this type of calculations is a problem of film noise. And we have to look on this, and this is what I'm doing. So yes, there is a solution for this decaying wave function. So if you focus on this, that what I'm trying to say, that if this is my slab and if I go deeper in the vacuum, so the decaying wave function somehow turns into the noise, and we can solve this problem. How? Let's say start, don't be afraid with the some complicated equations here. This is simple Concham. We can start with this with the simple Concham equation. So let's say if this is a second order differential equation, and there are two independent solutions are possible. One is the rising solution, other is the decaying one. So if I start integrating this equation and play a little bit with the integration direction of this equation, we can reduce this problem. But how? I have started with 3D complicated Concham equation, which is very much complicated to solve. So we can apply one trick of the Fourier transformation and convert this 3D to the simpler 1D equation. And first ignoring the lateral variations in the potential. And then we can compute this with the Numerov algorithm. So Numerov algorithm is a feasible solution. We can compute this equation to, and on the right, you see the computed eigenstates from the 1D with respect to the different Fourier components kx. So it means that the reverse integration, I mean that starting deep in the vacuum and integrating towards the surface. So this is the inverse integration direction that we can assume for this problem. So 1D Numerov seems to be a feasible way to go this. So now for this is the 1D, and now we opted this for the another 2D. So this we work with the non-trivial model of the potential. That for that I have my slab, applied electric field, and of course the lateral variations. And that you can clearly see here that how the lateral variations develop for the case of the 2D Gaussian potential. So this is the model of potential that we opted for our calculation of the eigenfunctions. And here you can see that when I opted this 2D model of the potential, so I have first computed the eigenfunctions from the global solver for each starting from the lowest eigenstate up to first, second, third, and I have plotted the 5 in series, the 5 eigenstates. And the interesting thing here is to convince you that yes, there is a noise, and which is clearly observed in the upper regions, right? So if we take this, let me plot this on the log scale, and then in the z line you can see if I take the one particular eigenfunction, so the wave function is decaying, that's fine, but after some time it runs into the noise, and this is what the problem of this decaying wave function in the deeper vacuum. So now if you are following my story until here, what I'm trying to say that let's say the position of my slab is somewhat defined in respect to these 3 regions. So region 3, this is far from the surface, and which is what I have shown the 1D Numerov without the lateral variations, and region 1 is which is quite close to the slab, where the DFT wave functions produce the reliable results, and region 2 is that what in between of these, where is the generalized Numerov that we have developed with the same analogy of the 1D Numerov. So this is the one equations that we had worked on here. The potential is no longer a scalar, but it's in vector operator. So basically now the task is to integrate the second order differential equation along the z direction in the reverse way, and recomputing the tails of the wave function so that we can trust on an algorithm that works at the local scale. So this was the key idea of this tail extrapolation. And so we have opted this equation and then start integrating in the reverse direction, which was a little complicated to solve it. And then we have compared this generalized Numerov results with the global solver, and we have seen that the generalized Numerov is stable against the high in plane Fourier components. So it means that we have to do something cleverly here. So how we have opted this thing. So first, if we just ignore the coefficients outside this, this is what is the one isomagnetic contour that come from the 1D Numerov, and here, for example, if I take the two magnitudes of the wave functions and rather to take all the high, just ignore the high in-plane Fourier components outside this boundary, set them 0 and just consider the coefficients inside this. Yeah, and this is my slab, and this is the, and then opting for the finite initial G starting G values. And this is how we work. So first we start with some initial coefficients in the real space, then we go back to the inverse space. And then we applied our these conditions of setting them 0 and just consider the coefficients with respect to 3 values, 3G range values, and this is what we call the Fourier filtering of our algorithm. And now we have the filtered coefficients in the inverse space, go back to the real space, again apply the generalized number of, until we get the final iteration, until the perfect matching of the solutions. So this was the brief summary that I have you, that how we choose the coefficients and how we get them. And then after getting the coefficients from the generalized number of, so if I see this in the XC plane, so this is what I get. This is the results from our extra. So we call this new scheme extra. Extra, I means the extrapolated of tail wire reverse algorithm. This is without any noise. And here you can see that if I match these solutions with the global one that I showed you initially, there was a noise. It match perfectly initially, but of course it will run into the noise. But this the extra, our new algorithm, it performs much better. Even we can't even see the noise, even up to 20 orders of magnitude in the vacuum. And this was a success of our new algorithm. So now until here I've shown we have a recipe. We can, so here we have first tested with the 2D model, and then we start with actual interfacing with the DFT Sphinx code. So this is the average potential that we took out for the rest of the calculations in the 3D with the high vacuum, and then we plot our final coefficients of this extra and the DFT on the same analogy that I have shown you before, that with the 10 orders of magnitude, how this wave functions initially matches, and this orange curve is come from the DFT. Yeah.
Just 2 minutes left.
Oh, I'm sorry. I would be quick here. And then we have opted this approach of the for the case for the tantalum and nickel. So for the tantalum, you can see this, the density of states is noisy from the DFT, and the density of state that we get from our extra, it's with no noise at all. And then we plotted, I'm sorry, then if we see at the comparison between the wave functions on the log scale, then we can clearly see that this extra performs, our new algorithm perform much better, and we can trust on it with respect, even for the case if there is some impurities on the nickel surface, which is tantalum in our case. So at this, I am already at the end. So initially I have shown you that this decaying wave function is a problem of the film, and the extra, that the stable algorithm that we have developed, it reduces solve this noise problem even with the 3D. And the actual matching confirms that we can trust on these solutions. And so here is the problem, here's the solution. Yeah. Thank you so much for your attention.
This is the perfect conclusion. Lee, you have a question? Can you please speak up? And thanks, Shalini, for a beautiful talk.
Sorry, my bad. My hand was still raised.
Ah, okay. So you don't have any questions?
I have too many.
Are there any other questions for Shalini? I can't see anyone with a raised hand. I mean, I think for the sake of time, we will move on, but this was really super pretty and really beautiful work. Thanks a lot.
Thank you.
And keep up the effort. It's coming. I really love the work.
Thank you so much.
Thanks. No worries. So the next speaker can start sharing their screen, please. Fred Danois, if you're not asleep. I know it's you, sorry. Yep, sorry, it's you. You are sharing the wrong screen.
Yeah, can you see?
Yeah, all good, yes.
Okay.
So Yue, I mean, this feels a bit like a Max Planck Institute for Hausenforschung session, but that's okay. Yue, please, the stage is yours.
Okay, thanks for the hosting. And I'm really from the APT group in MPIE, and this work was mainly supported by the Big Max and China Hongbao Fellowship. The title is Quantitative 3D Imaging of Chemical Short Range Order, mainly using the atom palm thermography. Actually, similarly with the process of a person experienced from the fertilized egg to a baby, the adult, and the elder, microstructure, especially during the ordering process, we can also observe the similar phenomenon from the very early ordering stage to the metastable or the stable precipitates. I think for now we are mostly familiar with the metastable or stable phases. And for the clusters or the medium range order, actually we can also utilize the advanced methods like the APT or even the STEM technique to detect this kind of tiny structure. But for the chemical short range order within a really tiny size, actually we are now pushing every techniques to probe this phenomenon. And so firstly, what is the chemical short range order? Especially for this chemical, it actually refers to the atoms of the specific elements self-organizing within this disordered crystalline matrix. This kind of particular atomic near neighbors can modify the mechanical or the functional properties of various materials. And however, due to its small size, typically within 3 nearest neighbors within about 1 nanometer size, so it actually have bring the challenging for the atomic scale characterization techniques. Here we would like to do this kind of research. We choose this N18% aluminum alloy as a candidate to develop this methodology. Why we choose this system? The mainly is because when the composition is located in this one, it actually is in the transition from the disordered BCC to ordered phases. And if we see at the higher temperature, we measured the electrical resistivity, we can see there is no change of this property. But if at the lower temperature, about 250 degrees, we actually can see an increasement for this value. It means there is a occurring of some kind of microstructure change, and it has been speculated to be related with the chemical short range order. And as comparison, if we see at the lower aluminum content, we cannot see any change at both temperatures. This kind of phenomenon was also called the K state, which has been observed in like the nickel-based or copper-based or even the medium or high entropy alloys. The similar phenomenon can be classified. So we would like to use our method to see whether we can find the chemical short range order signal from this system. We know the TM has done some work recently, and they are mainly based on this diffraction contrast or even the local compositional mapping. However, we know it typically gives us the 2D image, leading to the limitation in the measurement of the size or the morphology of chemical short range order domains, which I will compare our result with the TM later. For the APT, you must be familiar with this technique, which can provide us the 3D atomic positions and also the type of elements. And we know if we are along the specific orientation of the pole, we even can get the good depth resolution close to the atomic scale. So we will utilize this remaining the high quality signal for us to analyze this structure information to probe the chemical short range order. Here, for the experimental part, I show you this lower temperature, about the 250-degree annealing for 2 weeks. As an example, if we cut the sample from this 002 orientation and to get this APT data, if we zoom in, we can see the good atomic planes, and meaning the high depth resolution. And if we generate this SDMS curves within this using this small cube, the SDMS means can be generated by establishing the vectors between each atom and its neighbors. In 3D, if we plot it in the in this 1D in the direction, we can plot this 1D curves, the peak distance, meaning the atomic planes distance, and we actually know it belongs to the BCC structure. And if we plot this data using a smaller cube, and the millions of data will be generated to generate these similar curves, and we can analyze to check whether it belongs to the BCC or not. But before do that, we also have analyzed using the traditional method, like the frequency distribution of the nearest neighbors. And actually, we cannot get the concrete the SRO signal, which is which are expected. So we further use our machine learning method to do that. For the machine learning part, we firstly to build this pulsable crystal structure in advance. Based on the phase diagram of the previous literature, we have involved this BCC matrix DO3 and B2 type the chemical shell range order, and to generate its corresponding SDMS curves. For this process, we first need to build the super lattice in 3D, and then we shift the atoms to certain distance in XYZ. And for the Z, I use the smaller, the Gaussian standard deviation to simulate the better depth resolution. And further, we discard certain fraction of atoms to simulate the detect efficiencies. And to have a summary, we finally, by changing this XYZ standard deviation to, and also the detect efficiency, also to shift the peak to certain distance, and finally 10,000 simulated data can be generated, including these two features, and aluminum. So we utilize this data to training this 1D CN model after optimizing the hyperparameters, and we can get a recognition model. I will test it using the simulated data and the experimental data, but the experimental data has been made the pre-processing using mainly these curves, smoothing, and the background reduction. And here is the results. You can see for the training and the validation and test using the simulated data, we can almost get 100% accuracy. For the by using the experimental data to test it, we can see based on this ROC analysis, and we can see from this AOC value for the each class, this value is close to the 1, meaning the good model in this experimental data. However, we still would like to know how about the model performance on the large scale data. So we further to simulate the large scale APT simulation. I embedded the different sizes of those 3 domains into the BCC matrix, and by using our method, by using this 1 by 1 cubic nanometer cube to scan the model by, and the strata is 0.5 nanometer, we can see the predicted result in terms of the spatial distribution of atoms in XYZ, and with a higher PCC value close to about 0.8. And we further analyze the predicted morphology of these domains and also the site distributions. We can see the predicted morphology is close to the spherical one, and also the size distribution. We can see, although the model is not perfect, but it's still acceptable with a PCC value above 0.5, and it can be. If we generate a random data set, the model can also distinguish the predicted one and the random data set, meaning this model can also work well to distinguish the random clusters. And we further use the B2 structure to test it. Similarly, it can still also get a good predicted result in terms of the spatial distribution of atoms, morphology, and the set distributions. So we now push this model into this experimental data. Here is an example at the 250 degree, and the left hand is the predicted DO3 domains. If we zoom in, we can see the different colors, meaning the different domains, and to further analyze the morphology and the size, we can plot it in these two figures. The morphology is still close to the spherical one, and the size distribution actually is according to the log normal distribution. And you can see it accounts a large fraction. However, as comparison for the B2, we can see it accounts a lower fraction. And however, the morphology is still close to the spherical one and following the log normal distribution. However, we still need to ask, is seeing, is believing? Not necessarily. We still need to compare this results with the random data set. So we keep the atomic positions just to randomize the type of elements to build a random data set, and further to use the same method. Then we can plot the. Okay.
Just 1 minute left.
Yeah. Then we can plot the results into these two figures. For the DO3, we can see for the higher or lower temperature, they have the similar tendency with the random data set, and the PCC value is also close to 1, meaning this is the statistical DO3 domains we observed. For the B2, at the higher temperature, the PCC value is still close to 1, meaning the statistical one, but for the lower temperature, we can see a distinct difference from these columns, meaning there is a non-statistical B2 occurred in this aluminum system, and it also have changed the properties for the nano harness. Actually, considering the error bar, we cannot see too much difference, but for the resistivity, we can see a 5% increasement, matching well with the previous literature. So we can contribute it to the occurrence of B2. Although we have did some MCMD simulation, but we actually cannot get a good predictions due to the limitation of the user potentials. We are now working more to optimize this part. For the STEM result, actually we have did in our sample, and the conclusion is by using the STEM, the quantitative information actually cannot be achieved because the observed result will change with the thickness of the specimen. And also, in this case, we even cannot distinguish the DO3 or B2 using the STEM, because we cannot see it from these other orientations which should be observed. But this kind of phenomenon also has been met in other TM work when probing the chemical sharing order. To give you a brief summary, firstly, we propose a method to probe the different chemical sharing order in 3D, and we show our method in this aluminum system. And we also found the functional properties is actually more sensitive. And now we are also now pushing this method to other case. And finally, I would like to acknowledge my co-authors for this work. And thanks for your attention, and welcome the comments and suggestions.
Cool. Thanks, Yue. Fred, if you have a quick question, just go now.
Nice, though, thanks. I was wondering, can you deal with the different variants, orientation variants of the structure?
Yes, initially we have I have tested the different orientations, but for the DO3 or B2, if we would like to distinguish the 002 orientation is good. If from the 110 is impossible, and from the 111 the peak distance is too small for classification. Yeah.
Yep. Thanks. You guys can take it offline afterwards through the chat. Yue, can you stop sharing, please? And now, if I'm not mistaken, actually, Fred is supposed to give the next presentation.
Okay.
Thanks, Yue.
Can you see?
Yes, we can see, but it's hard to hear you, actually. It's not very loud. So you may have to speak closer to the microphone and speak louder. Yeah, try it. Go ahead.
Okay, it's not the right screen here.
So we see your slides.
Okay, great. So today I'm going to talk about some APT investigation of iron meteorite. This is part of a larger project that we conduct with colleagues in Marseille and in Paris. And so the context of the study, so I would just call it material processing, is that those iron meteorites, they were formed in the early ages of the young solar system by accretion of the solar dust to smaller, bigger and bigger bodies. And at some point, those bodies, they would just start heating up because of the decay of radioactive element 26. And so they would just melt down, and the heavy elements, which are mainly metals and siderophiles, they would come to the center and generate a nickel iron core. And once aluminum radioactivity is stopped, then those protoplanets, they will start cooling down very slowly. So slowly it's a question of kelvins per million years, and they will cool down to 100K. And during cooling, of course, you would, at the end of the cooling procedure, you would have a solid iron nickel alloy, which contains also cobalt, phosphorus, and sulfur. But I won't talk about these elements. And of course, during cooling, right after, let's say, 800 Celsius, then the melt would, the alloy would come in a two-phase region, the alpha ferrite and gamma austenites, and so it would decompose. And as it is very slow, it is supposed to be a equilibrium structure. And then a dual phase ferrite plus austenite would form with the ferrite growing along the 1,1 austenite plane, which leads to the famous Thomson-Widmanstatten structure that you can see here. And you can see it better if you take a sphere of the material, because you see the planes here, which are lying. This is the ferrite here, which lies in the 1,1 of the austenite. So that's for the microstructure. And so if we look closely at the microstructure, with such a slow cooling rate, we assume that phase transformation during cooling is under strict equilibrium conditions. And to check that, we measure the composition profile across retained austenite region. So on the left here, we have ferrite, on the right as well. And in the middle is retained austenite. Part of it has transformed to martensite because of cooling. And if we take a concentration profile from across this gamma region, what we see actually is what is called an M profile, which clearly indicates that the structure is not at equilibrium, because if it would be at equilibrium, we would have flat composition profiles. So even though cooling rate is very high, we still are not under equilibrium. But interestingly, we have regions on the edges here where we have this sort of gradient material gives us the possibility to explore the phase diagram of different iron-nickel alloys with very slow cooling rates. In particular, in this region, there's the composition of the alloy, which is a very important technological. So during cooling, the two-phase region is formed there, but as you reach temperature lower than 300, 400 Celsius, then this M-shaped profile is frozen, so the local composition wouldn't change. It's only some ordered phase that can appear at very low temperature, and this system is ideal for studying the generation of this low temperature ordered phase, in particular the L10 iron nickel, which is very interesting for its outstanding magnetic properties. So we were interested in this part of the concentration profile, and we decided to do atom probe analysis to see what was the microstructure here and to try to characterize the ordered phase appearing. So we did lift out. So this is a Cape York. This is one of the most famous meteorites. So here we have ferrite, we have austenite. Here we have the transformed austenite into martensite. And if you look in the Fib orientation, you can see that we have the interface, which is going down to the sample. And so if you look at from the side, the schematics, what we have is a chunk with austenite on top, ferrite on the lower part, and so we can prepare samples at different locations from the interface, and that's the way we explore this region here. So we use TKD to check the distance to the apex, the apex of the tip to the interface, and these are a few examples. There have been many more others, so we can explore really a large area of this region. And so if we come back to this M-shaped profile, this is a magnification. On this region here, really at the interface, we have the analysis where we have here the ferrite, which is nickel depleted, and we have a nickel enriched region. And if you measure the composition by atom probe, you find 55%, whereas EDS would just give a maximum 40%. This is because of the lateral resolution of EDS and also on the fact that the interface is bended. So you have mixed analysis of both phases, reducing the maximum value. But at least the peak concentration right at the interface in the first nanometers is 55 atomic percent nickel. If we go a little bit further, about 500 nanometers, then we have this sort of microstructure where we still have the very high nickel content region, and we have some region of ferrite here. I'm sorry, of iron depleted regions. We also have particles like a corridor between two gamma regions, and this we are about 43, 44 atomic percent in average in this region. When we go further, then we have in the average composition list, that region was 28 atomic percent. We're about 5 microns from the interface. Then we have much smaller nickel-rich particle embedded in iron-rich matrix. And if we go to the limit of the austenite to martensite region, where the composition is roughly 21 atomic percent, we have what looks like an homogeneous distribution of nickel atoms. However, the distribution is not exactly homogeneous, and to show that, I plotted the isosurface, so 30 atomic percent isosurface, which will separate nickel-rich and nickel-depleted region, and we see that we have very tiny precipitates, which are about 1 to 2 nanometer in radius. So this is for the morphology, and if we look at the composition, there we have I plotted different proxygrams, all in the same condition, so minus 10 to 10 nanometer from the interface, and we have a 30 atomic percent isosurface. And what we can clearly see here, for example, we have ferrite with a very low nickel, very low nickel content, and the rich region is slightly higher than 50 atomic percent. It's close to 55 atomic percent. If we go away from the interface, then we see that we have the matrix gets enriched in nickel, and also we come closer to the 50-50 iron nickel, and the same is observed when we get away. And so we clearly see here is the presence of the ordered L10 precipitate. Of course, those atom probe data do not show that it's ordered, but we also have field line microscopy and electron diffraction patterns that show that this is really the ordered phase. But if you look at the matrix, we don't see the 25 atomic percent, which is expected from the L12 iron 3 nickel. It's more likely to be 20 atomic percent. So I come to the conclusion that the meteoritic irons, even though they were cooled for very long, very slow cooling rates and for very long times, they are not at equilibrium. And this generated some gradient material that we can use to study the low temperature phase diagram. And we show that we clearly see the L10 structure in this gradient material, but probably we didn't see the Fe3 nickel. I said that we didn't see based first on the composition and also on the diffraction pattern, that we didn't see the order signature. So the next thing that we're going to do is to investigate other iron meteorites, in particular the one with nickel, the nickel-rich one. And if you want to have a look at Benjamin Class' presentation on Friday, he will show another Santa Catarina meteorite. And more importantly, we also want to investigate meteorites that experience different thermal history, in particular cooling rates, and some that have been reheated and cooled down at very fast. And so we expect to have much precise information about this ordered phase here. And with that, I want to thank you for your attention.
Thanks, Fred. Beautiful talk. I see that in the past 20 years that we've known each other, you still haven't changed the background of your slides, which I really can only admire. Are there any questions from the audience? So I will start with one. So you say that you estimate that at some point that the temperature is around 300 to 400 degrees, right?
Yes.
Where you have this phase separation taking place. So is this just based on, how was that estimated? Is it just based on the diffusivity that you would expect drops at some point below a certain point, or how did you estimate this?
Yeah, that's mobility, atomic mobility, because you won't diffuse for longer distance. So you just basically freeze the M-shaped profile.
Okay.
Of course, you still have some mobility, because if you want to produce the ordered phase, you need atomic mobility, but it's not enough to flatten the M-shaped profile.
Okay.
These are rough estimates.
Okay. Steve, ready? Yeah, please.
Hi, Fred. Thank you for that talk. I just have a question about the trace elements that you mentioned, which I think you said was phosphorus and cobalt.
Yeah.
Could you say something about how they are distributed and how they might affect some of those transformations, please?
Well, most of the phosphorus and sulfur is precipitate on the sulfides and phosphides. So the amount in the metal itself is very low. It's hundreds of ppm. And up to now, what we have seen is that at least phosphorus is mostly segregated at interfaces. So that's for sulfur, it's harder because we have an overlap between sulfur and oxygen can come from the instrument itself. So it's harder to conclude. But clearly, sulfur has a tendency to segregate at interfaces, not only alpha gamma, but also the internal interface in the oscillate.
Okay, thank you.
Thanks. Thanks for keeping to time as well, Fred. Can you stop sharing your beautiful screen? And then, so thanks again. If you have any more questions for Fred, please feel free to use the chat box, and we can move on to Lisa's talk. Hi, Lisa. Good morning. We can't hear you. Can you?
Can you hear me now?
Oh, we can hear you now, indeed.
Okay, great, thank you.
No worries.
So I'll get started then.
Yes, please.
So my name is Ryan. I am a PhD student at Imperial College London. Today I'll be talking about atom probe tomography of neutron irradiated UK PWR reactor pressure vessel steel. So firstly, a little bit of background. So here we have a figure of the installed nuclear capacity in the UK. Now, the UK has set an ambitious national target of net zero carbon emissions by 2050. And nuclear power has a huge potential to help in meeting this ambitious objective. However, one big issue with nuclear power is the life expectancy. If we can increase the life expectancy of a nuclear power plant, we can increase the amount of low carbon energy that the nuclear power plant can produce. So in order to increase the life expectancy, we need to identify the life limiting components, and we need to work out a way to improve them. Now, the life limiting component of a nuclear reactor, the PWR reactor, is the reactor pressure vessel itself. And here we have a figure of a reactor pressure vessel. So inside the reactor pressure vessel, it's an extreme environment with heat, pressure, and irradiation. And the pressure vessel steel, over time, it degrades. It becomes more brittle, which is not what we want. And when the reactor pressure vessel steel is unfit for service, that is when the nuclear power plant is decommissioned. So in this figure here, we have an image of a reactor. And inside the reactor, we have a surveillance capsule. Now, a surveillance capsule is a capsule inside the reactor. And this is where we put surveillance samples. And we put surveillance samples in here to most accurately mimic the conditions of the reactor pressure vessel steel itself. So surveillance samples themselves are the gold standard of samples when looking at reactor pressure vessel steel. However, one issue with surveillance samples is that the reactor pressure vessel steel itself is experiencing pressure, and this is something that is not present in the surveillance sample. So we are simulating the heat and the irradiation damage, but not the pressure. So moving on to this project and the samples that we're looking at, we have 4 samples here, 2 baseline samples and 2 irradiated surveillance samples. And the irradiated surveillance samples consist of 2 conditions, an unstrained condition and a pre-strained condition that's been pre-strained to 5%. And this pre-strained condition is, it's there to better mimic the conditions that's experienced inside the reactor pressure vessel. And this is something that's seldom seen in the literature. There's very few experiments on pre-strained steel that's been irradiated, and there's also very few surveillance sample experiments. So this represents a really unique opportunity to have a look at what's going on inside the reactor pressure vessel steel. Okay, so moving on to the atom probe tomography itself. So we used a gallium fib to prepare the samples, and the method that we used in running the experiment was in line with standard procedure, except for our voltage mode runs, we did use a slightly higher temperature of 55 Kelvin, which is in contrast to the more standard 50 Kelvin in the literature. And this is simply to increase the yield, as we had issues with our steel samples in the atom probe, and we wasn't getting the yield that we would like. Now, we ran most of our samples in voltage mode, and we did this because we're particularly interested in the silicon and phosphorus inside the samples. And silicon and phosphorus are very prone to migration effects. That's present most notably in laser mode, although it does still exist in voltage mode. So primarily, we've been looking at voltage mode to minimize the migration effects on the silicon and the phosphorus in particular. Now, when analyzing RPV steel, when we're looking for irradiation-induced clusters. Now, the standard method for doing this is the maximum separation method. So that was the first step. We applied the maximum separation method here. However, what you can see is, aside from a dislocation and a carbide, which has been picked up here, there's very little clustering going on, and this is not what we expect. We would expect the whole sample to be visible with clusters. Now, there's a few reasons why the maximum separation method has failed in this case, and that is due to the fact that we're using a surveillance sample. So the temperature of irradiation is much higher, and also the flux is considerably lower compared to other samples that are not surveillance samples. What this leads to is that the steel we're looking at is at a much earlier stage in the process of irradiation. So the maximum separation method here is inadequate. Okay, so here is a reconstruction of one of the samples, and we're looking at the phosphorus here. So I've made the phosphorus larger here so we can see it, and we can see that there's a dislocation in the top left here, and we can see that dislocation has trapped some of the phosphorus. And we also see a cluster in the bottom right that doesn't appear to have any high concentrations of phosphorus here. I've included this image in particular to show that phosphorus is something that we're very interested in, and it's has the potential to be the major difference between the unstrained condition and the pre-strained condition. However, we're only getting around 200 phosphorus ions per sample. So sample size is a very limiting factor here, and it is quite an issue. So we don't have these large clusters that other stills may have that have been irradiated in lab conditions. But this does represent a really unique opportunity to look at early stage clustering, so the very small clusters that aren't picked up with standard methods. And to look at these early stage clusters, we've decided to use a radial distribution function. Now, a radial distribution function, it takes a target atom. In this case, we have targeted all the silicon atoms, all the manganese atoms, all the nickel atoms, and all the copper atoms. And we've chosen these 4 elements as these are common clustering elements. So the radial distribution function takes the target atom and it measures the concentration of all the elements at as a function of radius. So what we have here are 2 graphs. We have the unstrained condition on the left and we have the pre-strained condition in the center. Now we can see that there is a big difference in the phosphorus concentration at lower radii. So in the unstrained condition, we are seeing much more phosphorus at lower radii. And one possible reason for this is that the pre-straining is increasing the dislocation density, and these dislocations are trapping the phosphorus. Therefore, when we look at these early stage clusters, we're not finding as much phosphorus in the pre-strained case, whereas in the unstrained case, the phosphorus is available and we see it segregating into these early stage clusters. However, there are quite a few issues with this. One is the thermal migration, which I discussed about slightly before. A laser mode sample that was run showing it's reconstruction showing silicon. We can see the distorted shape. We would expect this to be fairly uniform, but it's not. And this is due to the thermal migration of the silicon. Silicon and phosphorus are both very light elements, and they're very prone to this. So one of the issues with the radial distribution function is that because we included silicon as a target, the worry here is that silicon and phosphorus are both migrating to the same location, and that's coming up as a higher concentration. So to fix this, we removed the silicon from the target. Next up are dislocations. So the radial distribution function is averaging out over the entire sample, and it doesn't differentiate between dislocations and clusters. It will just show the concentrations. And what we find is that the dislocations are trapping the phosphorus, and there's a very high concentration of phosphorus at dislocations. So the next step was to remove any dislocation that we could see. So here we have the graph on the left. We have the radial distribution function, but we removed the target of silicon and we removed any visible dislocation. And we can still see an increase in phosphorus concentrations at lower radii in the unstrained case compared to the pre-strained case. And this is a comparison graph here. And it's quite a noticeable difference, although the sample size is still quite low. And we're still only getting around 200 phosphorus atoms per sample. So the next thing that we did, so if we look at the sample here on the left, we have created a region of interest. And this region of interest is between the cylindrical region of interest between a dislocation and a cluster, where the z-axis is going up, going to the top left. And the reason we've done this is that this sample in particular presents an opportunity to look at the interaction between the dislocation and the cluster, as they're both visible in the same sample. And one of the reasons we are interested in this is because if our hypothesis is correct that the phosphorus is being trapped by the dislocations, then what we would expect to see here is the phosphorus being present in the dislocation and actually not being present in the cluster, even though we would expect phosphorus to be present in the cluster in the absence of a dislocation. And that's what we see here. So if we look at the right, this is a line composition profile. And we can see that to the right-hand side of the graph is the dislocation. We see an increase in phosphorus. And to the left-hand side of the graph, we see an increase in copper, but very little increase in phosphorus, which suggests that the phosphorus is preferentially appearing at dislocations and not at clusters. The reason this is of importance is because going back to the reactor pressure vessel itself, is that if we can find a way to increase the life expectancy of these pressure vessels, we can extend the life expectancy, we can extend the lifespan of a nuclear reactor. And understanding how the strain, the combined effects of the strain and the irradiation damage will help us better understand the material. And this is something that hasn't really been done yet. And here we have tried to come up with a method that can be used in the future to analyze these early stage clusters. So to conclude, a radial distribution function is used to measure solute composition of early stage clustering in irradiated steel. At lower radii, phosphorus is present in lower concentrations in the strain condition, which may affect cluster composition. Phosphorus is possibly trapped more by the extra dislocations in the pre-strain samples, and therefore is less associated with copper, manganese, and nickel. And that's us seen in clusters. And the hypothesis is that the pre-strain material has an inherently higher dislocation density, which needs to be proven by other methods. Ongoing and future work with TEM and XRD is planned to measure dislocation densities of each condition. Are there any questions? And thank you for listening.
Thanks, Ryan. And thanks for keeping to time. This is really nice of you. Are there any questions for Ryan? Maybe I'll start. So has there been work demonstrating phosphorized segregation to dislocations? Is this something that's expected?
So we are expecting this, and we also see this very clearly in the samples. And one of the interesting things about the radial distribution function is it actually is, when we're looking at the samples, it's often our first sign that we can see a dislocation is we see a huge spike in the phosphorus, which sort of encourages us to look closer and try and find these dislocations.
But the radial distribution function would be averaging over, like in 3 dimensions isotropically. Are there not like maybe methods that could be giving you some more like direct evidence that this segregation is elongated in one direction, like some descriptors like the SOAP or something that people have been using quite a lot to try and work this out?
Yes, so there's a possibility to sort of refine what we're doing. This is just very sort of early stage. Our idea was mostly to look at the clusters, and that would be sort of, we would expect that in 3 dimensions, we would expect the common solute elements to be clustering and being closer together, which should be picked up with the radial distribution function.
Which it is, yeah, it's good. Cool, okay, thanks a lot. I see no other questions, so I think we can move on to the next. Gang has a question. Gang, please go ahead. You have a minute.
Just a quick question about you observe the phosphorus segregation in these locations. What happens to carbon? Have you looked at the carbon? Whether or not the carbon is segregated there, or how does carbon distributed? Do you got my sound? No.
I can hear you. Ryan,
Yes.
could you hear Gang?
So the question is about the carbon distributions, whether or not there's a carbon segregation is the dislocations by only phosphorus.
Yeah, so that's a very interesting point. We did look at carbon as well. We didn't see much carbon, and one of the reasons is that a lot of our carbon is contained in these carbides here. Sorry, I'll just screen this. So there's lots of carbides present in our samples, and the carbon is being contained in these carbides. There's not much going on outside of the carbides. But yes, that is something that we did look at, and something that is also quite lacking in modeling, is that very little modeling that we could find is being done about sort of how carbon is moving in these sort of situations.
Okay, thank you.
Okay, thanks. Please stop sharing your screen, Ryan. Thank you. Thanks a lot. Thanks for the nice talk. The final talk of the session is given by Tinting Chu. I'm probably butchering your last name. I'm sorry. So please share your slides.
Okay.
Can you hear me now?
We can hear you. Yes, no worries.
Okay. Also, my slides is normal here.
Yep. Go ahead.
Okay.
Yep,
Thank you
it's
very
all good.
much.
Thank you.
Okay, thank you. Hello everybody, and I'm from Carlos Heights, Shanghai, and now is application supervisor here in China. And today I want to introduce dice laser FIB and how to use it for the fabrication of atom probe specimens. And first, in this page, we show the portfolio of size microscopy. It covers multi-scale characterization for multi-scale research, like we can from millimeter to nanometer in the scale. And if we add instrument experiments into our instruments, we can also do research from 2-dimensional to 4-dimensional. And confocal here of size has a very high resolution, about 120 nanometer. And besides, it can allow us to get 3D characterization in the surface. And the XIM, the X-ray microscope here and here are very professional on 3D undestructive tomography. Here, the nanoscale XIM here has a resolution based on 15 nanometers. And today my topic will focus on FIB laser, or we will call it laser FIB. And the name of it is will also be crossbeam laser. We just combine laser here in our analog with the FIB SEM system. The SEM can help us to get very high resolved images, and while FIB column here can cover the job of like meaning or deposition. And the laser here can do massive material removal very fast. And in the following slides, we will talk about these points. My agenda today is just 2 general topics. The first is about the crossbeam and its application on atom probe preparation. And the second topic is about the laser and how laser can help us to make an atom probe. And first we come to Zeiss crossbeam. Zeiss crossbeam right now are all equipped with ion scalped FIB column. It's a gallium focused ion beam column with high throughput, excellent low kV performance, and long-term stability. It features high current up to 100 nanoampere with excellent spot profiles. And also it has high resolution better than 3 nanometers. It can help us to do some precise structuring tasks, and also can get some image of high resolved FIB image like this. The voltage range of ion scalped is from 500 volt to 30 kilovolt. And this kind of low ion energies, like 2 kilovolt, 1 kilovolt, or even 500 volt, is usually used for fine polishing of our sample, like the CM lamella or atom probe, for the minimum amorphous layer and damage. When designing this ion scalped FIB column, special care was taken to current stability. Right now, we have a current stability longer than 72 hours. It's very important for the long-term experiments like 3D tomography or battery sample production like this. Our ion scalped has a very high performance in low ion energy. Like here, we show the examples and the images we taken at 5 kilovolt, 2 kilovolt, and even 1 kilovolt. We can see that the region of interest is imaged with great details. And so in the next step, we can, the milling objects can be positioned here or here very precisely for further thinning of the lamella, or like our atom probe. These 2 features are very important to fabricate very thin lamellas or atom probe of extraordinary quality. The E-beam right now used in our size crossbeam is from Gemini columns. The same with the FE SDMV the size has. And the Gemini objective lens is a non-emission lens. This means that there will be no magnetic field here below the polar piece, so we can take some very high resolved image on magnetic samples. And the feed process can be monitored live at highest available resolution with any detector by the E-beam. But if we come to the magnetic emission lens here like this, there will be strong magnetic field at the sample. So it will not be that easy to take any image on the magnetic samples. But also if the I-beam and the E-beam are turned on at the same time, the magnetic field will affect the I-beam here, and will result in not that good milling or deposition. These here are 6 images of inland signals correspond to the frames of a movie we taken when Phoebe is painting a spiral on the silicon. Here we can see that the spiral has a line width narrowed down to 20 nanometer. So we can see here that even if it's a live imaging, we can still have a very high resolution. Also, this is a inland detector. We can also use a secondary electron detector to get the live monitor. So the patterning process can be imaged live at the best instrument resolution and with any detector. And maybe many of you are very familiar with E-beam deposition to depth protection like carbon, platinum. And here we, in size crossbeam, we can use E-beam to depth the marker. Like this complex mark here, we depth by E-beam with platinum. Here, the specific site or the ROI, or we call it the region of interest, is just below this point. And so with this kind of process, in the whole process of the milling, like 20 milling or fine polish, we can easily to make sure that our ROI is still here by this white line up on our sample. The advantages of using E-beam induced deposition to depth marks are first, it's very easy to locate our specific site. Also, it's very easy for us to make sure that our ROI is still in our sample along the whole processing. And since it's the E-beam deposition, so there will be no damage to the sample compared to I-beam depth. And the last but not least, the time here is very short. It's very fast for E-beam to depth this kind of line. It's just 5 seconds. So here I want to share 2 applications of the crossbeam depth on low KV, the low ion energy, and the E-beam depth marker. First, it's about the low ion energy. Maybe many of you has known that the standard process to fabricate an atom probe in FIB-SEM system is first we will dap platinum or carbon on our sample, and then is the 20 milling fine polish. And after this, we can use the nano probe to lift this lamella out and transfer it to the coupon. The sample we use here is nickel steel high entropy alloy. And after this, we will welding the lamella to the coupon and sharpening, cut the needle and sharpening, thinning, or even polishing the probe to the final probe like this. And this probe, we take the atom probe chromatography. After the result, we can see here that there is no gallium detected in this atom. So we can just say that there is very little implantation in our probe. And why can we get such little implantation in our probe? Is because we start from 10 kilovolt and use a low kV like 2 kilovolt or 1 kilovolt to clean the probe. These two methods can make sure that the probe will have very little implantation in our sample. And when it comes to the e-beam depth markup, we use aluminum alloy here as an example. It's a little difficult for us to locate the grain boundary, like here in the aluminum. So after we find this boundary, we use e-beam deposition to dep a platinum line here up on the grain boundary. And then after this, we can use e-beam and ion beam to dep carbon protection. So along all these process, we can use like this, the PT line here changed to a white dot. We can use this kind of white dot to make sure that our grain boundary is still in the center of the pillar to make sure the success will finally come in this process. And the next is what's new in Zeiss crossbeam laser. So first, what is laser FIB? Laser FIB is a combination of laser and the FIB-SEM system. The laser is typically a 5-second laser. With this kind of laser, we can do a massive material removal, like we can create cross sections up to several millimeters, both in radius and in depth. And because of this, we can gain rapid access to deeply buried structures, like from 50 micrometers to 1 millimeter for the following FIB-SEM analysis. Then due to the ultra short laser pulse, we use here the 5-second laser here. There will be minimal damage and the heat affected zone in our sample. And what's more special in Zeiss crossbeam laser is shown here in this picture. We can see that the laser works done in a dedicated chamber here to avoid the contamination of main instruments. Like the photograph we show here, laser is attached to the airlock, and the main chamber is still just for the same FIB use. The laser we use is a diode pumped solid-state green laser with a wavelength of 550 nanometer. The safety of the laser is laser class 1, so it's very safe for us to use this kind of crossbeam laser in our lab. And most important, maybe most of you will care about, is that the spore size. The spore size of laser is better than 15 micrometer. So it's still much larger than gallium beam spot. But when we come to the material remove rate here, we can see in the chart, here is the laser and here is the other beam like gallium, helium, and even xenon plasma. Laser is the fastest, even in the several orders of magnitude. We can see the example here. We do the remove in the silicon by laser. The removed material here is about 1.1 cubic millimeter. The whole time we took is just about 5 minutes. So it's very fast. And also we can see the picture attached here. The ball is very smooth. So it's fast and also it's very easy. And how can laser help us to prepare an atom probe? Here I will use the deep buried ROI2 as an example. So as an example, the ROI is about 100 micrometers deep. And first we will use laser to create this micro lamella. and to make sure that the ROI is in it. Then we will use FIB to mill to the desired depth until the ROI is close to the surface. It's also accessible for FIB SEM work like the following lifter out process. Here is an example on silicon sample. We use laser to create a micro lamella. The length is about 400 micrometers, and the depth is 350 micrometers. And we can see the thickness here at the top of this micro lamella is just 10 micrometer. And both of this side was done with coarse milling and fine polishing. This total time is just 80 seconds. Then we can use FIB to remove the material to the depth of the desired depth of the laser processed chunk, and the two standard FIB lamellas were prepared. And also this kind is just we can go to 75 micrometers, but also we can to use FIB milling to like 80 micrometers or even 100 micrometers. So it can help us to get atom probe from different depths. After this, we can use the narrow probe to transfer the lamella onto the silicon coupon, and we can follow with the thinning and the shaping or the polishing steps to make it to be an atom probe like this. And so that is also a very new and faster way to fabricate site-specific probe for the local electrode atom probe. We can show here that laser can help us to prepare molds like this. Just in 29 seconds, it's very fast. And we can see the out is about 500 micrometers. The inner one is about 38 micrometers. If we use gallium ion beam to prepare this kind of mold, maybe it will take, let's just say hours or days, but with laser, it's just 30 seconds. And then we can use FIB to shaping and polish it and clean to a probe like this. Here is just an atom probe. We can also fabricate several probes in one sample for one time. Like here, it's 4 atom probes here, and the distance between these two atoms or these two atoms are 350 micrometers. If this kind of process can be used to do the local electrode atom probe. And back to this example, from this mode and to this kind of probe, it just takes us less than 3 hours to get this kind of probe. So it's very quickly, or it's very fast. And come to the summary now. We can with this crossbeam laser, the high performance of the low ion energy, we cannot just take a high resolved image of our lamellas or atom probes, but can also make atom probes without any gallium detected. Also, the SEM image, we can use SEM to image live while your FIB is milling. Also, the E-beam can be used to depth some special marks we want to help us to recognize the site, the specific site. And we come to the laser. Laser is a very faster way to remove massive material. So with this kind of technique, we can to create the atom probe from deeply buried ROI, and also we can do some site-specific work on our sample because the position accuracy of laser is better than 2 micrometers. Okay, that's all. Thank you.
Okay, thank you. Are there any specific questions for Ting? Yes, this is a good question from Nikita.
We can watch the laser field work by the CCD camera, but not like the SEM.
Yep. Okay. I guess that would saturate the detectors, right? I mean, you're probably emitting a lot of material. And
yes, like a CCD.
Yeah. Yeah, sure. I understand. Okay, thanks. Fred, do you want to
remove the material here is in this airlock, and we will use some vacuum jet to pump this material away. But there will be some lift in the chamber, so sometimes we may need to use like alcohol to wipe it. Like there is a glass here. Just between the laser and the sample, the glass is very easy to get dirty, so we will need some way to make it clean. But the glass, it can be renewable.
Okay.
Yes, like this.
Okay, like a consumable. Fred, do you want to ask your question, please?
Yeah, I had this short question about, did you estimate the thermal damage on the tip?
Sorry, the sound is too.
Did you estimate the thermal damage that is made by the laser? How deep is it extending?
Yes, might be several micrometers.
Okay.
Do you mean this? So the
yeah, I think that's what he means. Yes.
Yeah.
Is that okay, Fred? Are you satisfied?
Did you run some specimens already prepared this way?
Sorry, I can't hear.
Did you manage to run specimens in the atom probe that were prepared with this mode and FABE method?
Yes.
The specimen that you showed for the atom probe, did you actually run them?
Me or my colleagues?
Yeah, your colleagues. Not these ones from the lift out, the ones that you made afterwards with the mode. Yes, these ones.
Sorry, I can make sure of that. This is the result for my colleagues, but I think they can do this on the real amorphous process. Just like this, I think it's okay for the tomography.
But you don't have results. You cannot show results from those specimens. Okay.
Yes.
Okay. Thank you. Fred, are you okay with that? Good. Okay, cool. So I'm now tasked with closing this session. Thanks to all of the speakers and all of the people have with questions and exchanges. So we start again tomorrow at 2 a.m. my time, 8 a.m. Beijing time, and whichever time in your own time zone. I wish you a pleasant day, afternoon, night, sweet dreams to most of us who are going to go sleep, even though it's 12 p.m. And see you tomorrow. Take care.